but we are not going to be talking about those very specific problems. Here we are talking about, in general, optimization problem solving. So I will give you a very overall kind of a hand waving argument of why or what we think that what's happening in a GA that's causing the whole process to reach near the optima. So this comes with the concept of Holland schema, or these days we just call it just schema, because Holland was the first person who, well, he conceived the whole method and he suggested an argument of why such methods work. So he came up with this idea called schema. The schema that you see that I've written here, the plural of schema is called schemata. Okay. Now a schema is nothing but a similarity template. What's happening here? Later. What did I do? Okay. So schema is actually represents a set of strings with certain similarities in them. For example, let's say that I have a 4-bit string that represents a particular x, and x, so then there are total 16 solutions, right, with 4 bits, 2 times 2 times 2 times 2, and with the decoded values are shown here. When you decode all zeros you get 0, when you decode all ones you get 15, right, and any other will be coming in between, and they always come in an integer, right. We've seen that before. Now let's say I represent a schema. So schema is represented by 0 and 1, that's already there at one position. Now there is a third quantity that can come, and that's a star. So a star represents either a 1 or a 0. So at every place there can be either a 0, 1 or a star. Okay, so it's a triplet. One of them can come at every place. So then you can write arbitrarily anything between 0, 1 and star at every place, you get a schema. So this is one schema where 1 is in the very most significant place, and then star, star, star. So as I said, star represents both 0 and 1. So this is in the schema level, but then we have to go down to the string level to figure out how many strings does this schema represent. So there are 2 options at the second place. It could be either a 0 or a 1 here. 2 options at the third place, 2 options at the fourth place. So how many total options we have? 8, right? 2 times 2 times 2. And one of the strings, for example, is 1 and all zeros. 1, 0, 1, 0. So anything you put here as 0 and 1 is fine, as long as the first bit, the most significant bit, is 1. So the schema represents whenever there is a fixed thing like 0 or 1, those you cannot change. Only the stars can be changed. Okay. So now let's look at and see here what are those 8 solutions or the decoded values that the first schema represents. Can someone tell me? So most significant bit is 1, and I told you that there will be 8 strings that this schema represents. 8 strings means 8 decoded values. So what are these decoded values? 8 to 15, right? So 8 onwards to 15, all these 8 solutions, 8 to 15, 8 solutions are represented by 1 star star star. So now you have a way, a schema actually says not 1, but a class, a set of strings that a particular schema can represent. Okay. So with every schema, there exists at least one or more competing schema. It's competitor. So if I have a 1 here, what's this competitor? 0. And then if I say H0 is that schema, 0 and all star, what are the decoded values that this schema represents? 0 to 7. You'll see that because they are competitor, there is no overlap. No strings is common to these 2 things, right? So if I tell you 1, 0, star, star, first question, how many decoded values would it represent, or how many strings would it represent? 4, because there are 2 stars. And how many competing schema does it has? 2? 4. Same number. Okay, 4, including itself. So you have 1, 0. So what are those? 1, 0 I already told you. So its competitors are 0, 0, star, star, 0, 1, star, star, and 1, 1, star, star. So there are total 4 partitions when you have order 2 schemas. So now I need to define certain things with the schema. So you see the schema, if you start with a fixed bit right from the most significant bit in a contiguous manner, it represents a contiguous space in these in the search space. So the fact is, I told you 1, 0, and star, star. Can you tell me? You didn't tell me yet. Okay, 1, 0, star, star. What are the decoded values now? So it could be 1 0 0 0 2 1 0 1 1. So what are these two bounds? 8 to 11. Everybody agrees? So there are 4, 8, 9, 10, 11. So these are the 4 strings that 1 0 star star will represent. So obviously it represents 1/4 of the entire search space. When you have 1 here, there are 2 options, 2 competitors, 1 and 0. So 1 represents half of it, the other represents the other half. When I have 1 0, then there are 4 partitions, equal partitions, so there will be 1/4 of the entire search space is represented by that particular schema. Is that okay? All right. There can be a schema with star 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 1 as well. So what are the decoded values of that it represents? Star 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 1. All the odd numbers, right? So like these shaded ones that I have 1, 3, 5, 7, like this. It's not a very interesting schema, but it is also a schema. It again represents 50% of the entire search space because of 1 fixed bits. Now if I have to optimize this function, for example, if I have to maximize this function, then which of these 2 schema are important, more important? Huh? Well, you just came. You don't know what is schema yet. So you need to first know what is schema. So this part represents 0 and all star. This part represents 1 star star star. So if I'm maximizing this function, right? So what schemata is more important? 0 and all star. Everybody agrees? Why is that? That's because most of the high function value, this is the function value or fitness, high fitness solutions are on the left side of this space, not on the right side. So now you can think of that if I have an initial population which is uniformly distributed, let's say with a population size 4. So I'm on an average expecting 2 here and 2 there, right? When you randomly create population members. Now what GA should do is instead of emphasizing this schema, it should emphasize that schema. What it means that with generations now, I should be able to see more zeros in the most significant bit. If that's not happening, then some parameter setting like population size, the crossover probability, the mutation probability, the operators that you have used, the single point or 2 point or whatever, the combination is not working. If eventually you have lots of 1s in the first place, because lots of 1s means all your points are moving here. But if you have this schema getting more and more copies, that means much of your solutions from here is moving here, right? And that's what we want. Now once all of them or most of them move here, what should happen next? Well, let's look at, I can go into now 2 fixed bits kind of schema, right? So then 0 is now there. Okay, so that means all of them has 0 at the first place. Now I can split it again at the second place. It could be a 0 or 1. So I can now think of order 2 schema where it could be 0 0 or 0 1. So which one do you think? 0 0, because that covers 0 1 2 and 3, right? This is the 1/4 of the entire search space, which will be represented by 0 0 star star. So you see, and that is better region than 0 1 star star, because 0 1 star star is 4 5 6 7, and their average fitness is somewhere here, and this schema's average fitness is somewhere there. So this should win. So now next you should observe that the second bit is getting more and more zeros. You see now how the GA will eventually converge, and now you have to go to the third level, and then there will be some dichotomy which way to go. So this is how, starting from most significant bit, which actually changes the function value by a large amount if you be, and it's also easy for you to look at through the schema processing point of view. Eventually there will be a convergence bit by bit, and you get closer to the optima. So this was the original idea that Holland had. Now in order to be a bit more quantitative, what Holland says is, let's define 2 parameters. One is called the defining length, delta H, which is actually the difference between the outermost defined positions of a schema. So for example, if I have a schema like this, okay, as I said, a schema, every place can have a 0 1 or a star. So this is a valid schema. So what are the two outermost fixed bits? Outermost means the leftmost and the rightmost. So it's 1 here, which is in the second position, first position, second position, and 0 here is the rightmost fixed bit, and its position is 1, 2, 3, 4, right? So rightmost is 4, leftmost is 2, so the difference between them is the defining length, which is 4 minus 2 or 2. So what is the defining length of this schema? What are the two outermost defined positions? 8. There is no 8, there are only 4 bits. So this is the first bit, second bit, third bit, fourth bit. So what bit is this? First bit. And what is the left and rightmost? The same one. So leftmost is 1, first bit, rightmost is first bit. So what's the difference? 0. So this one has a defining length 0. Same is this. Okay? This one has a defining length of 2. Is that clear to everybody? Yeah. It's the difference between the two outermost defined positions. So what are the defined positions? This one is second position. This one is the fourth position. Okay, so 4 minus 2 is 2. Is that clear? So basically I'm saying between the two outermost defined positions, how many cross sites are there? That's what I'm saying, because this will come handy for the crossover operator when we analyze. So there is one cross site can be here, another cross site can be there. Here there is 0 cross site that comes between the two defined positions. Okay. The second thing that he defined is called order of a schema. I already mentioned order 1, order 2. So order basically says how many fixed bits are there in my schema. So how many fixed bits are here? 1 and 2. So there are 2 fixed bits. Star is not a fixed bit. Star you have not defined yet. How many fixed bits are here? 1. So these are order 1 schema, order 1 schema, order 2 schema, the same one here. Okay. Is that clear, the difference between order and the defining length? Okay, so this will come handy. I'm not giving you the entire analysis of how we come to this expression. This was kind of modified by Goldberg from Holland's calculations, and he came up with this inequality which used to be known as Schema Theorem, but later on there are more precise Schema Theorems that came out, but they have much more terms over here added, but that makes it very ugly, and to analyze what I'm going to analyze a little difficult. So that's why I said that we just take this as a guidance. We don't take it very, very seriously. So let me just, but this gives you a good ballpark figure of what's going to happen, all right? And that's what we're interested in knowing here. So if you have 1-point crossover operator, which we talked about, a single site, and you swap the right-hand side information, and a bitwise mutation, which you already discussed, your 0 becomes changed to 1, 1 becomes changed to 0, right? With a probability PM, and crossover is done with a probability PC. Let's say we're dealing with L-bit strings, and the fitness of every strings can be denoted by F. Okay. Then he says that, or he calculated as that if MHT is the number of copies of a particular schema H. So first you have to fix the schema. Let's say that schema is that 1 and all star, or any of the schemas that you can write. That's called H, let's say. Okay. So if I then count how many copies that schema has in my initial population or at my current generation, looking at the whole population, if I count how many strings does this schema get represented in this population, I'll take an example soon, so you'll see what I'm talking about. So this is a number. This will be an integer, actually. How many copies? It could be 0 copies. If there are 0 copies, this formula, this theorem has no way to tell you whether it will going to have an increased number of copies. That's the drawback of this. But the complete schema theorem has that ability, but the equations are more complex. So you got to have m greater than or equal to 1. Okay? And then FH is the fitness of the schema. The way it's defined, it's that it's the average fitness of all the strings in my population that is represented by the schema. Again, I'll take an example and you'll see what I mean. F bar is the average fitness of the population, not with this schema. All the members that I have in the population, if I take an average fitness. So this ratio actually tells us how good is this schema. If I'm maximizing, which this particular selection operator, oh, I forgot to mention, this one is assumed proportionate selection, which we have not talked about, but I'll just very briefly mention to you what is proportionate selection after I finish this slide. So this actually allocates number of copies based on the fitness of a particular solution. So that's the fitness here. And so if FH by F bar is greater than 1, then that says this particular schema is very good, is above average. Okay. So higher the number, the better it is. Okay. So let's assume it this way now. And then it gets modified. So this actually, the product here actually says how many copies the H will have in the next generation by the selection operation only. After selection, how many copies will be obtained? And then here is a term that modifies that and gives us the how many copies will remain after I apply crossover and mutation. You see here, this is always less than 1. So it assumes that crossover and mutation, this is the crossover part, that's the mutation part, always destroys the schema that you have. But that's not always true. You can actually create by the crossover mechanism, by the mutation mechanism, because I showed you that you had a better solution, right? In at least one example. So the creative part is missing here because that's the messy part. So that's the part I'm missing. Actually, I'm not writing here. So this is very, very conservative estimate, and that's why Goldberg put a greater than equal to sign here, saying whatever this gives you as an estimate, you will actually have more than that because of the additional part that I have not included here, right? Okay, so now it says the crossover probability is here. Delta H by L minus 1 gives an idea of the survival probability of the schema, because I told you these are basically the number of sites you have in between the two outermost positions. So I'm assuming if any cross site falls in between, you're going to destroy that schema. So this is basically, sorry, not the survival, it was the destruction probability of the schema multiplied by PC, because you're not doing 100% of the time. 1 minus that somehow gives you the survival probability, and this comes from the mutational effect. PM times OH destroys the schema. That's the probability by which the schema gets destroyed. So this part here, this plus this, is the total destruction probability. 1 minus this is the survival probability. Multiplied to this tells you how many copies will survive. So this is a very rough estimate. Now what this tells us is that if we have FH much greater than F bar, that means this is greater than 1. And if we have a delta H that is very small, so you have chosen a schema where the defining length is small. What does it mean? You see the defining length is 0 when you have an order 1 schema, right? So very tight, not tight, very small number. Yeah, it's tight actually, very tight schema. So that means the difference between the two outermost position is not very high. Okay, they are close together, the defined positions. And order OH is small. So that means 1 bit, 1 fixed bit, or 2 fixed bit, or 3 fixed bits at the most. So they are very small order. If you have small delta H and small OH, this quantity is going to be large. This being large, so let's say this is greater than 1. Let's say this is 2. And this one here is very small. Let's say 0.1. So I've got 1 minus 0.1, which is 0.9. So 0.9 times 2 gives me 1.8. So, and then if this is 1 even, if you had 1 copy now, this formula says at least you're going to have 1.8 copies in the next generation, which means at least 2 copies, because this is a greater than equal to, and this has to be an integer. So at least there will be 2 copies. So that means that says that H for which this is low, this is high, is called a building block. It's going to grow. Okay, with generation it's going to grow. So now in your problem, if you identify H, you can investigate by this formula and say whether this schema is going to grow or not. And schema actually represents a contiguous region or some region in the search space, right? It need not be contiguous, it could be periodic as we have shown. Whether this is going to grow or not. So if for some schema this grows, you know that optima is right there. Okay? If the schema is not growing, that means it's not in a good place. So maybe you can exclude that from your further consideration. You may not create any new solution there. So it's very powerful that way. Okay? Let me now define this proportionate selection. I think I have it afterwards, possibly. No, this was at the end. Let me quickly check where I have the proportionate selection. Yes, before the application. So let me go up. I think this is page 61, if you want to go there. I will just define the proportionate selection and come out from there. Yeah. Okay. So here is the proportionate selection, or also known as the roulette wheel selection. So this is how the whole genetic algorithm started. Okay. We didn't have tournament selection back then. Okay. So this was the selection operator which was used in place of tournament selection. So what it is, let's say I've got five population members. Each one of them I've got a fitness, and I'm maximizing. So there are certain things you have to assume before you want to use this operator. First thing, it has to be a maximization problem. Second thing is all your function values have to be positive, non-negative. 0 is allowed, but non-negative, negative is not allowed. Okay? So when you have these two restrictions satisfied, then you can use this selection. Maximization and non-negative function values, fitness values. Okay? So let's say I've got 5 population members and their fitnesses are such that if I take a roulette wheel and kind of mark the circumference of the roulette wheel based on the proportion of the fitness in the population, right? So this basically says if I sum the whole fitness, this one represent, let's say, about 20% of the sum fitness. Okay? This one is about that, slightly less than, maybe 18%. This one may be 10%, but this one may be 40% or something like that, right? And this one is maybe 2% or 5%, something like that. So that sums up to be 100%. So if you have all these fitnesses, they're all positive. Okay? You sum it up and then take a ratio, right? Fitness by the sum, fitness by the sum. You mark the roulette wheel based on that ratio. So which one is the best here? You're maximizing. 3 is the best. Next is 1. Next is 5. Worst is 2. Right? So that kind of gives you an idea of the best one is allocated a large amount of area in the roulette wheel. And like you've seen in a roulette wheel, what they do, they spin it, right? And eventually there is a pointer and it will come to stop. Whichever this pointer points to, you take a copy of that and put into your mating pool.
The probability of multiplying of 3 would be more than...
Yes. So now, if you have a 5 population size, you will be spinning it 5 times. Every time whichever is picked, you put it in the mating pool. Okay? So 3 will have more chances, more copies in the mating pool. 2 will have maybe 0 copies. You can be unlucky and get 1. Okay? But it's very small probability that you will get 1. So the number of copies that you get in the mating pool is in proportion to the fitness you have. That's why it's called proportional selection. Like we do in tournament selection, not this way. Tournament selection, we shuffle it, take the top 2, and decide which is the best. Next 2, decide which is the best. So that whole thing is replaced by this operator. And this also has a probabilistic way of saying or allocating more copies to better individuals, less copies to less individuals. It has this couple of restrictions. Not only that, it has some other issues. Like computationally, it is a little expensive because you have to sum up all of them, find all the probabilities, and then simulate these roulette wheel kind of concept. So computationally more demanding. And it also has some scaling issues, which Goldberg nicely described in his book. A lot of scaling issues it has. By that I mean, if all of them have very similar fitness, which will happen towards the end, when you are converging, all of them are very close to the optima and have very similar fitness, then what happens here? Everybody has more or less the same area covered. And then when you spin it 5 times, almost each one of them will get 1 copy each. So as if you have not done any selection. Whatever was there in the population, same is the mating pool. So there is no selection effect. And you know selection is the main operator that provides the direction. So your search becomes not random, but not a very guided search at the end. So it loses its convergence properties. On the other hand, in the beginning sometimes when you're particularly dealing with constraints and you're using a penalty function approach, what you may have is that one individual can be a super individual. One individual's fitness can be very high compared to rest of the population members. So now that individual, if that's the number 3, this is going to occupy most of the area because it's really a super individual, very high fitness, others are very small. So let's say 3 has got a fitness of 100 and others are around 1 to 5. Then when you do proportionately, what's going to happen? This is going to take care of 90% of the region almost, and then the others will be small, small. So if you do 5 times, chances are that that individual will be picked all the 5 times. So now you've got a mating pool with no diversity. All of them are the same. If you do crossover between 2 same individuals, you don't get anything new. Only thing you're relying on is mutation. And as I mentioned, that's not a very search intensive operator. So your whole search process also slows down in the beginning. So it has the scaling issues, it has the computational problem, but then a good 10, 15, 20 years in the beginning, these operators dominated the field of GA. Then people came up with this tournament selection, which is good in every way. So there was a 1990 paper that Goldberg and I have written doing analysis of different selection operators and concluded that these operators is not good in any respect. Either because of that paper or people have realized on their own, now hardly anybody use this method. But the theory is very good to do with this because it's in proportion. So you could do nice theories, but tournament selection, because of 2, 2, 2 at a time, it's very difficult to do math. Okay, so all the mathematically oriented people in genetic algorithms still do math based on this operator, saying that okay, whatever is true here is probably going to be true for other operators as well. That's not 100% true, but it allows you to do theory. It becomes a little manageable. Okay, so yeah, I've skipped this example, but let's say I just want to get back to the theory part. So that proportionate selection is used here for the theory as well. So you see now the fitness will be assigned based on the proportion, and that's what we have here. Let's take an example to just explain how we can utilize the schema theorem. Let's say I've got a problem to maximize, which is sine x. Sine x, you know, it's a periodic function. But I'm restricting myself between 0 to pi. So how does the function look between 0 to pi? I can take a sketch here. 0 to, so let's first put here sine x. And so when x is equal to, let's say I put pi here and I put 2 pi here. So how does it go? Right? This is one cycle of sine x. And we are restricting ourselves between 0 to pi. So that means this is our range, lower bound, upper bound. And I'm maximizing this function. So where is the optima? Right at pi by 2. Okay, so here is the optima. Okay, so imagine always that this is the problem I'm trying to solve now. Okay, so in order to do this, let me go back to the slide, and I have decided to do 5-bit string. Okay, and I have created a population of size 4. So 4 individuals are created here. Okay, so these zeros and ones are created at random. Okay. Can we move back to the slide, please? So we have so 5 bits are used here. So these zeros and ones are actually created by flipping a coin. Okay, if it comes head, when I flip one time, I put a 1 here. If I get tail, I put a 0 here. You can also do this experiment at home. Okay, so this is how I get the first string, second string, third string, fourth string. Now I take the decoded value of that. So 1 plus 8, 9. This is 4 plus 16, 20. 1 is 1 only, and here you get 26. So you can have numbers here from 0 to 31 with 5 bits, right? We have seen that before. Okay, now we have to map it between 0 to pi. Remember the mapping formula we talked about, right? So when you map this number between 0 and pi, this one maps to 0.912, this one maps to 2.027, and pi is what? 3.1. So none of this number will be more than 3.14 and less than 0. Okay, so because the mapping ensures that, so we mapped it. Okay, now after we mapped, now we got the x. Now we don't need the strings. We've got the x. We can assign the fitness, and it's an unconstrained problem. So we can go and substitute x equal to 0.912 radian. When you put it there, sine of that will give me this, and similarly this will give me this, and so on and so forth. Okay, so this is the evaluation part. Just for the sake of computing it later, I have actually taken the average of these population fitness. Average of these becomes 0.569. We'll just remember that, right? Now we are applying 1 iterations of proportionate selection, 1 point crossover, and bitwise mutation. Okay, in order to do proportionate selection, what you do, I told you that this fitness has to be divided by the sum of the fitnesses. And then I would multiply with the number of population members. So basically, instead of dividing it by sum of fitness, I am dividing it by the average fitness. Okay, so when I do that, instead of the probabilities, I straight away get how many copies each individual should get in the mating pool on an average. If I divide it by sum of fitness, I get the probability of copies, number of copies. But here, when I then multiply by the number of populations, it tells me the expected number. So these are actually expected number of copies that I am expecting in my mating pool using the proportionate selection. So it should get 1.39, 1.58, 0.18, 0.85. Now you know what I mean, how it's computed. It's just fi by f this one divided by this, and I get this number. Okay. So you see that the one, which is the best one here? Second one, having the largest value. And the optimum would be pi by 2, and that will be 1, right? Sine pi by 2 is 1. So that's my optimal function value. But here, I don't have the optimum yet. These are randomly created, but this is already 0.898. Okay? So that's the best one, and the worst one is 0.101. You see the best one should get about 1.58 copies. And this one over here, the next best should get 1.39. The worst will get 0.18, and this one will get 0.85 copies. Actually, I do simulation of the roulette wheel, okay? And I got 1 copy of that, and I got 2 copies of this, because this covers more than 50% of the region, so I get 2 copies. And this one gets 0 copies, and this one gets 1 copy. So this is how I get 4 copies. And see, they are pretty close. These are theoretical expected numbers, and this is what actually I got. So if you simulate it many times, it will follow, their average will follow this. That's what it says. Okay, so let's get 1 copy from here and put it here. Let's get 2 copies of this and put it here. And so this one got deleted. And let's get 1 copy and put it here. So this is my mating pool, where the best gets 2 copies, and the worst get no copies, and these 2 individuals get 1 copy each. So that at least provided me some direction. Because this one is pretty worse, it's 0.101 fitness, so very low in the fitness, this one didn't pass through the selection phase. Okay? So that's the idea of selection. Now I copy this population in the next page, and I'm going to do now a 1-point crossover. How do we do 1-point crossover? We have to pair them up first. So let's say I do these 2. We make sure that the same two copies are not crossed, because then I'm not going to get anything new. So I've just taken these 2 as one pair, that 2 as another pair. Now I've used a crossover probability of 1. So that means 100% crossover will take place. There is just population of size 4, only 2 pairs to cross. I don't want to just cross 1 and the not other, then it's a probability of 50%. So I said, okay, let's do all. So 100% crossover probability, both will get crossed. So now in order to cross this, I also need another thing. What is that? Where shall I cross it? So there are 4 positions. You see 1, 2, 3, 4. 4 positions to cross. In this case, I have randomly chosen the cross site number 3. So go third site, 1, 2, 3. So I'm going to cross here. And now I'm going to have 2 strings with 0, 1, 0, 0, 0, and 1, 0, 1, 0, 1. Okay? Now these are 2 new strings. You see, they're different from here. Now take these 2, and I have chosen randomly cross site 2. So here, so I'll get 1, 0, 0, 1, 0, and 1, 1, 1, 0, 0. Again, 2 new strings. Now that I've got the new strings, I need to do what now? Mutation. Okay? Actually, I have not used mutation because it's only 5-bit, so I didn't use mutation. But I could use a very small mutation as well. Okay? So if I had to do mutation, then I could just go with that probability bit by bit and flip. If the mutation come out to be okay, then I'm going to be changing 0 to 1. Or if it happens to be that I'll be mutating this bit 1, it will become 0. Okay? So I have not done anything that. So this becomes my final population after 1 iteration of this GA. Is that clear? Let's see what has happened in this 1 iteration, because many things were randomly created. Let's see what has happened. And if you do it, you will probably observe very similar behavior as well. So when I decode this, I get 8, right? This one is 21, 18, 28. Now again, I map it using the same mapping formula, 0 to pi. I get this x values. With this x, I can compute sine x, the fitness, and I get this. Okay? First thing to notice is the average fitness of this. It's 0.710. What did I have before? 0.569. So initially, it's not a magic. It will happen. Why does it happen? That there is an increase in the average fitness? Because the bad ones are deleted, right? So, and then you are using, again, a crossover, which is actually mixing the good properties of 2 solutions. So in general, you will expect, initially at least, that your average fitness is increasing. That means you are going towards near the good region. Then, of course, it will slow down. Sometimes you may not even be increasing. Sometimes you may be dropping a little bit, but that's not a problem. Then you can come back up again. But initially, you observe that. Okay? Yeah?
Can we apply this roulette wheel minimization?
You have to do some transformation. You have to convert the minimization to a maximization problem. One of the ways people suggested was, if you have to do, let's say, minimize fx, you convert this problem to a maximize 1 over 1 plus fx. So that way your minimum here becomes the maximum of this function. So this becomes your fitness function, capital, let me call it capital Fx. Okay. Some other people do, so this is one version. Another way people do is maximize some big number minus fx. So you are converting, basically it's a minus, you multiplied by minus sign. Remember the way we converted by duality principle, but because negative values are not allowed for roulette wheel selection, you add a very large number. So this is supposed to be an idea of f max, but if you know f max, you know the opt solution. So you usually don't know f max, so you have to keep it a large number. Okay, I prefer this one if you have to use than this c minus fx, because it requires the knowledge of c. Then you need to supply a good c. There are other transformations as well, okay, that exist, but basically you need to convert minimization problem to a maximization problem. Okay, getting back to the slide again. All right, so first thing I showed you is that there is an increase in the average fitness. So that means we are moving in the right direction. And then now this becomes your population, and then you will be doing again proportionate selection, crossover mutation, and things are going to improve thereon. Okay, let's try to do it based on the schema theorem that we just discussed. Let's say I take a schema H1, which is 1, 0, and star, star, star. So what region does it represent? Let me get back to the paper here. So what schema does this one represent? So we have 1, 0, all star, star. So what is the lowest decoded value and highest decoded value that you can get with this? So how will you get the lowest value? When you have all zeros. So what is the decoded value? All zeros. This will be 16. And all ones here. So we are talking about this. What is that decoded to? 1 plus 2, 3, 3 plus 8, 3 plus 4, 7, 7 plus 16, 23. So if I map it, now I have to map it to x. So we'll be somewhere here. So this is my entire space now. This is my entire space. Now when I do half, what is this one? 0 and 4 stars. What is that one? 1 and all stars. Okay, we're talking about 1, 0. So we need to split this again. What is this one here? 1, 0, star, star, star. And so this one is the optima, 16, and this one is the 23 that we'll get when you map it, it will come to this. So basically we are talking about this region here. This contiguous region is represented by this schema. Is that okay? Everyone is in agreement with me? So it's this 1/4 of the entire space. Why did I choose this as a schema to investigate? Why not, for example, this schema? So why didn't I choose 1, 1, star, star, star? Right. So this schema actually entails or contains the maxima. So I expect this schema to have an increased number of copies in my generation. If not, then something I have done is not right.
So, but here we are selecting the schema based on the knowledge of the function.
Yeah. So because I see the function, but in general, how you're going to use this is you have a problem, and you're saying I'm expecting the optimum to be between this and this in my search space. Really, is there the optimum or something you want to see, or some knowledge you have that says the diameter should be between this and this? Now you create a schema out of that, and then you observe your GA runs. Is it increasing the number of copies in that region or not? So that's the idea. You may not know exactly where it is. That's why I'm not saying, in this case, the optima lies in one of the boundaries of the schema. But I know that maybe the optima is there, so I'm trying to see, is my GA that I've developed is putting increasingly more copies to that schema or not? Okay. You can then compute everything and do, or the best thing would be if you are just doing it for pedagogical purposes, so you're trying to learn how this algorithm is working, then you're going to change your parameters and rerun and see how is that new parameter is doing. You can study, you can also print out how many copies are represented by that schema that you are thinking where the optimum is. Or if you're doing it for a test problem where you know where the optimum is, you want to now investigate the behavior of an algorithm and seeing is this algorithm trying to continuously increase the number of representative solutions there or not? How fast it's increasing? So you can then change your parameters and maybe choose the one that does a maximum increase in the growth. So these are some very nice and scientific way of choosing parameter sets. But then you need to know what is the schema concept before you can do that, right? So here I'm assuming that I have an idea of where to look at. I'm not pinpointing here is the optima, but I'm saying, okay, this is a good place where the optima can lie, and now I'm seeing how my algorithm is going to do there, right? So if I try to follow up the formula that I gave you, so let's first look at this particular schema then. How many copies does it have in my original population? So here's my original population. Remember, schema is 1, 0, and star, star, star. So how many copies does it have? Just this one, 1, 0, and all star. Others do not have 1, 0 at the first two places. I only look at the fixed bits. Stars can mean anything, right? 0 or 1. So this one only satisfies or represents that schema. So there is only one copy. So MHT is 1, just 1, right? What's his fitness? 0.898. Okay. So first thing was how many copies? So that's 1, MHT. Second one is the fitness, goes in the numerator, 0.898, divided by the average fitness of the population. So the fitness schema is 0.898, and the average is 0.569. So I take the ratio of this by that. But let's say I had taken a schema that was, let's say, 1 and star, 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 star. So 1 and all star. So if that was my schema, 1 and all stars, how many strings does it represent? So this one and that one. Okay. Now how will I, so it has one fitness here, another fitness there. How will I compute FH? The average of the two. So this plus this divided by 2, average of the two. If there were 3, this plus this divided by 3. So that's the average you get. So that's the average. Here I have just one, average is same as that one, right? So that's that. And then this is the population average fitness, considering the whole population, not with the schema. Okay, so you see that this is a very good schema, right? Because its average fitness is greater than 1. Now let's look at here. 1 minus the crossover probability, which is 1. What is the defining length of this schema? 1. Why? Second is the rightmost, 1 is the leftmost. So 2 minus 1 or 1. And then L minus 1. L is 5 bits. So L is 5, so 5 minus 1. Minus mutation probability 0, order, there are 2. It doesn't matter actually, even if you do an error here, because you're multiplying by 0. But to make it correct, you have to have order, which is 2. So 2 here. So if you compute the whole thing, this one turns out to be 1.184. So it says you started with 1. Now the number of copies you are expecting in the next iteration, after one generation of the whole thing, you should expect 2 copies. Because anything more than 1 will be 2, right? And there is an additive part which I didn't put here to make things a little simple, but it's 1.184 more than that. So let's see how many copies we have in the next generation population with 1, 0. We got 1 here, we got 1 there, 2 of them. Okay. So this gives me an idea of a lower bound on how many copies. It doesn't say, it could have been 3 as well, okay, because it just says greater than equal to. You need the full formula in order to be pinpointing how many, but that's really a lot of terms that has to be added. But in our literature that exists, if you're interested, you can search for schema theorem in Google, and you will get eventually to the more elaborate formula there. But this can give you an idea. Now I bet if you try at home, the other schema, 1, 1, star, star, star. Is there a copy in the first one? Yeah, I've got a copy here. 1, 1, star, 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 and repeat the process. You will see that it will be less than 1. Okay, so in general. Now some of the schemas, it can be slightly more than 1 or less than 1 in the initial generations, and then it may reduce as you go along. So this happens, this also depends on what generations you are doing this. So that's why I said you need to probably, if you write a GA code, no GA code at this point has this kind of calculations, but if you then add some addendum to the code that from the population you will do this additional calculation of schema processing, and you are going to print out whatever schema you supply, you are going to print out their number, how they are growing with generation. Then if you plot, you will see that some of them will keep on growing and getting stabilized. Others may be growing for a while and then dropping. Other may be dropping right from the beginning. So this gives you an idea the whole competition that goes on between the schema. So what Holland and Goldberg early on, very early on, suggested is how genetic algorithms work is that these low order short and high above average schema, they are called building blocks. They grow to become higher order building blocks. So this 1 and all star will then become 1 0 all stars, and then it will become maybe 1 0 0 all stars, and eventually you have a convergence to the optima, right? This is a very simple hand waving way of saying how GAs work, but it's much more complicated than that, obviously. Okay, now if you look at the theory, because I know some of you are interested in theory, you came and told me, there are basically 3 ways the theory have been going on, but now some of them have survived, some of them have died down because they reached a dead end. But let me tell you how it all started. First of all, theory is hard to do in GA compared to classical point-by-point based methods. Why? That's because here we're talking about stochastic methods. Nothing is deterministic. If you give me a deterministic rule that this point can only go to steepest descent, for example, this point, no matter who of you are applying a steepest descent for a given problem starting from a particular point, every one of you will get the same answer. That's why it's easy for me to grade, because I know where you're supposed to go. If you have not gone, means you have done something wrong, right? These methods, very difficult to grade because all of you will get different, slightly different answer. Intermediate points also at the end, you may not all get to the same point eventually. So these are difficult to do. Plus, there is a population to track, not just one point, right? And so these are difficult to do. But people have still tried to manage in many different ways. One approach people have been following is the engineering approach, which is mainly Goldberg and his students. And there are some other people came along. It's functional decomposition approaches. So you look at one aspect of the whole process at a time by fixing other aspects. For example, if you want to study, like I said that we did the selection study, right, comparing different selection schemes, what did you do with the crossover and mutation? We just kept it fixed. We didn't assume anything. We just said our generation ends with the mating pool. So we are not creating anything new. Then our goal is, if I keep doing the selection, eventually our current best should take over the population. So let's see how fast it takes over. If it takes over very fast, means it's a very good and very fast moving selection operator. So, and then there are some other metric we came up with. So this is one way to do. Then we did a crossover study alone by fixing other things. There are some argument why such a thing is approximate, because unless you do the all of them together, you're actually not looking at the interactions. But this kind of engineering approach, one at a time kind of concept, had given us a lot of insights, a lot of thumb rule kind of results that we can use in practice. On the other hand, the statistical dynamics approach came from mainly people from physics who looks at the whole distribution of fitness. So for example, if you take an initial population, every member you compute a function value, you now can look at a distribution of how the fitness value is distributed. And so a distribution can be represented by a mean, by a standard deviation and higher order moments like kurtosis and all that, skewness and everything, right? So now let's say even if you take the two things, the mean and the standard deviation of your current population, there will be a mean and a standard deviation. Can you do a theoretical analysis when you apply one generation of all these operators, you get a new fitness distribution? Can you guess what would be the new, or can you write a mathematical expression of how the mean is going to grow, how the standard deviation is going to grow? Then instead of actually simulating the GA, you can simulate those equations, and then you can see how the GA is going to perform. They were able to do quite a bit of work, but then one of the things that needed here was the actual function value. What is the fitness function that you're trying to maximize? The engineering approach did not need that, but this one needed fitness function, and they couldn't do more than very simple like linear or quadratic. They couldn't do more than that. So that's why this has come to a dead end. I don't think anybody is working in this area anymore. Okay, but that gave us a lot of ideas in the beginning of the importance of crossover, selection, and everything. The one that's still there is the dynamical systems approach, which is more mathematical approach. So first one is more engineering, second one is more physics related, third one is more math. Okay, so the dynamical system approach considers the whole G as a Markov chain. Okay, those of you who know Markov chain, it's a dynamical systems where time dependent equations will come, but a transition of current state from the previous, it only depends on the previous state, not the states before previous. That's called a Markov chain. And GA is like that. You only need to look at current population to decide what is going to be the next population. You don't look at 2 generations before. What was that? That affected the previous generation, but not the current one. So it's a Markov chain. So then Markov chain has lots of literature, right? So you can then use the waiting time, the first time you hit the maxima, all these kind of calculations you can do. But then you need to model the crossover operator, mutation operator, which becomes a little tedious. But there are very nice minds, mathematics oriented, and people have written books on this area. A lot of literature and still going on. Okay? The foundations of GA workshop I mentioned to you, FOGA, there will be a lot of representative people from these fields and talking about theories. So the bottom line is, if you take any arbitrary problem, okay, there we have a convergence proof that is like this, called asymptotic proof, that eventually, if you have a GA that has a mutation, okay, with a finite probability, not a zero mutation like I used in the small problem, but it's a finite mutation probability, non-zero, and the mutation has the property that from any point when you mutate, you can go to any other point in the search space. There could be very small probabilities, but non-zero probabilities of getting from any point to any point by mutation. Crossover is not needed for this proof. Okay? If you have that kind of mutation, and if you have elite preservation, did I mention that? Elite preservation probably I didn't mention. What that is that, so you have done the crossover selection, crossover mutation, and you got the new population, right? Now an additional thing you do, which is called elite preservation, where you take the best individual from the previous generation, previous population, simply copy it here at the expense of one of them. So maybe the worst one you take out and put this one there. Or somehow you utilize the best individual of previous generation in your mutation crossover operator that goes intact to the next. So you don't want to lose the best solution you had before. That's called the elite preservation. So that way, if you print out or plot the best fitness versus generation, you will never have a dip, because either it will stay if you have not found anything new, or it will continue to grow, right, if you're maximizing. So that fitness will never go down. So you can have monotonic performances. So that's a very good thing. And also for the proof, this kind of thing is needed. So if you have this elite preservation, that means something that you have now, you can never go below that. And there's a mutation operator that says any point to any point you can go. It's also intuitive that eventually this process will take you to the optima, right? But there is a mathematical proof that says, yes, it will. So what we are and where we are at this point, it can be any problem that you are giving it. As long as you have a elite preservation and a finite mutation probability with the mutation operator I mentioned to you, there is a convergence proof. Eventually, it will take you to the optima. What it doesn't tell you is when, right? How many generations it's going to. It's an asymptotic proof. So if your function value is 100 maximum, it will asymptotically approach 100. Eventually, at infinite time, after infinite time, you're going to get there. But when you do in practice, it will not take infinite time, but you have to have patience to get there. So that kind of proof is backing up our algorithm. But these kinds of proofs are enough for some mathematically oriented people to start paying attention, because now at least if I keep running, it actually says you're going in the right direction if you have these properties. Okay. Similar thing happened with simulated annealing back in mid 80s, where they were doing simulated annealing, but someone came up with such an asymptotic proof, and a lot of people started to pay attention to simulated annealing. So after this proof came out in 1995 by a person called Rudolph from Germany, and after that we had a lot of mathematicians came to our field and still working on getting better and better proof. Now, this is for any arbitrary function, right? Does NFL theorem is valid here? So am I violating NFL theorem when I'm talking about this? Remember, one of the things in NFL theorem was that you got to have a finite resource and finite time for application for each of them when you're comparing two methods. But this one doesn't say that it's going to converge in a finite time. It's asymptotic. So with this algorithm and this theory, the NFL is not violated, because NFL theorem is, I cannot apply NFL. to this, because it says, if you tell me for this problem I want a result in 1 hour, this theory says, no, I cannot guarantee that, because you have to give me infinite time to get there. Okay, so NFL is not violated with this. And to me, being practitioner, applied to a lot of problems, this is not much useful, except to know that I'm working with an algorithm that has that property that it improves. It eventually will get there. But now I try to do customization, do various things so that I can do much better job of converging in a finite time. But then I have a different algorithm for different methods. So it's good to have at the back of our minds, but this one doesn't help me in any way. Okay? But if I'm dealing with a mathematician, if I'm in a trouble, explaining him my algorithm, I show them this proof, and suddenly I see them paying attention to what I'm saying. So it straightens things up, few things. So if you know these things, it's just all a matter of parlance, the language that you're talking to, whom you're talking. I would not talk about this to a practitioner, okay, because this doesn't help me to size my population. This doesn't help me to choose a particular operator. For example, crossover is even not mentioned here, right, in the proof. But I consider crossover is the main search operator. So there are a few things, but then these are good things to know at the back. But I think the breadth of ES applications so far in many, many different problems leaves us with no doubt that whatever we're doing with all this crossover mutation selection is all working towards getting to the optima. Okay. Population size, symbol is funny here. Population size in proportion to the number of variables. Usually all this theory, the functional approach that we talked about, that gives us this kind of idea. We usually say 5 to 10 times the number of variables if you're starting with a random initial population. We should use crossover very high probability with 0.8 to 0.1. As I said to some of you, I always use around 0.9. Okay? And low mutation probability, usually mutation should not be done with too much aggressiveness. 1 over n, where n is the number of variables, is a good idea. 1 variable per solution you may want to mutate. So 1 bit per whole string you may want to mutate. So it is 1 over n or 1 over L. There are some theory that says when you do selection, you are leaving out some members and making 2 or 3 copies of some members, so you're actually losing variance, losing diversity. Your crossover and mutation should be such that the diversity is replenished, is supplied. So the loss of variance due to selection should be supplied by the crossover and mutation. And someone talked to me about exploration and exploitation. This is the main issue here in this parameter setting. The selection does the exploitation. You have current population members. There are some good ones, there are some bad ones. How many copies you want to give the good ones is an exploiter. How much you want to exploit your current population. Okay? If you want to do too much, like take the best one and make all of them the same, that's too much. Then you cannot do crossover, right? And if you just do 1 copy, then it's also too little. So how much to do? That's the exploitation extent. On the other hand, the crossover, if you do 1 point, there is not much exploration. If you do 2 point, a bit more. If you do a uniform crossover, which is like every bit you take it with a random probability of 0.5, you really have a very large search, a very large exploration that's going on. 2 have to be balanced in order for it to work properly. Okay, and there are some theoretical studies based on how to balance and what to do. So this is basically the whole evolutionary optimization is an act of exploitation versus exploitation. Not only evolutionary, this is with any population-based approaches. Okay, it's that. So exploitation is how many copies of the best you are going to give to the next in the mating pool. How much you want to exploit your current population. So you've got some members are good, some members are bad in your current population. And what selection is doing is saying, okay, I'm going to give 2 copies of the best and maybe near best solutions, 0 copies to the worst and its near about solutions, and on an average 1 copies to the intermediate solutions, right? So that's one. I might come and say, no, I'm going to give 3 copies to all the best and nearby. So then I have to sacrifice a lot more from the worst side, right, in order to have 3 copies. So that's more exploitation. Okay, what you want to do? Are you going to do 2, 3, or even I talked to you about 1.5? You may have to go down that level also. Versus, am I going to do a single point crossover where the structure is mostly kept, right? If I do 2 point, I've done a bit more swapping. more kind of more rigorous swapping that I'm doing. Then if I go to the one extreme, which is called the uniform, where if you have two parents, bit by bit, you just go and with probability 0.5, you take from one of the parents. So there is no structure that will be left. Okay, I have a slide, one of the slides after the theory. I think you can note it down. I'm not going to go to that one now, but that's page 62. I have an example of the uniform crossover. You can see that you don't have any structure left there. So that is more and more exploration. How much you want to do, how much you want to explore the current population that you have in its vicinity. So you got to have a balance of the two in order for GS to work. For simple operators, we have done some studies like one-point crossover and bitwise mutation. We actually didn't do the mutation, just crossover and selection. And we came up with a nice, I don't think I have it over here. No, I don't have it here. It's too much for this class. But we have got a balance between the exploration and exploitation with a mathematical function that says if you satisfy these inequality constraints, you are making a balance. If you are not, you are too much. You are not balancing the two. And then we go to simulation and show such a curve, and we show that, yes, it's following that. So it's really an act of exploitation versus exploration, the whole issue. Now, these are all verbal that I'm saying now. I'm not giving any mathematical formula. It's not possible for us to do for every algorithm such a fine line with exploitation exploration. It comes with experience somewhat and your understanding of the whole algorithm. So these parameters that I've told you here, if you follow, it kind of does that. Okay, so if you do a binary tournament selection where two at a time and take the best and use high crossover probability and low mutation like this, you automatically make that balance. Okay, then there is another issue of population size. So this again makes that balance when you do the population size in proportion to the number of variables. So mutation ensures traversing every state. Crossover is useful in complex problems, but if it's a very simple problem, you don't need crossover. Mutation can do that. Mutation you can consider always like a perturbation. And if you are in the right hill and you're maximizing, if you get a point in that hill, mutation can help you go up and get there. But if you have multiple hills, and then mutation cannot take you to the global or take you to a better hill from your current position. So mutation is more like a hill climbing approach. When you bring in crossover, it has the power of recombining two hills to get it to fall into a better hill. Okay, so you need that. So when you have a multimodal problem or other more complex problems, you need the crossover. So that's our conclusions from all the studies that we have done in the past. Okay, so let's leave that last part. So this is the end of this last lecture 4 that I had. So now I take a 5 minutes break, maybe tea is waiting, and then we assemble again. Okay? All right. Yeah.
If I get 2 or 3 same kind of functional values, then what kind of tree I select?
You can just take any one of them. Some elite preservation, they do not just the one, the best one, but let's say top 5% members, population members copied.
That can be
Start? Okay. So we'll now start with lecture 5, where we'll talk about advanced methods. Okay, so far we only looked at binary coded GA and some theoretical underpinnings of why they should work, and then some example problems of where we have applied and showed you their broad applicability, right? Now let's go and see some real parameter evolutionary methods, because in practice we would get mixed integer programming that we said. Some of the variables will be real, some of the variables will be discrete, but compared to the classical literature, the evolutionary is just opposite in the sense that, well, the whole classical algorithms are developed for real parameters, as we have seen, so that the derivatives can be computed. So if you have a real parameter problem, you can straight away use the classical algorithms, right? If you have a discrete problem, that means some of your variables are discrete, then you have to use those fix-ups like branch and bound and stuff like that. And I showed you that it can be a little difficult, and you have solved some problems yourself and you see how many loops you get into and all that, right? GA is natural for discrete variables, because if you're using binary coded GA, you are anyway splitting your whole space into few points, like 2 to the power something, right? If you're taking 5 bits, you are thinking of only 32 points. So although it could be a continuous search space, but you are breaking it up into 32 points. If you increase it to 10 bits, you can have 1024 points. You can go to 20 bits, 50 bits to get any precision, but it's still a finite number of points. So if you have a discrete space problem, right, discrete variable problem, binary coded GAs are natural. But if you have a real parameter, what do? You are actually doing an approximation, right, because you are anyway approximating your real space into discrete space and finding a near optimal solution, unless one of your solutions hit by chance the optimum. Okay? But now we'll talk about directly dealing with real parameter optimization problems where you don't need the binary coding, right? You can straight away use a GA concept to deal with real parameters. This has started after the binary coded GAs have been developed. So there are some algorithms that are really motivated by how binary coded GAs work, how the binary coded GAs, if I apply to real coded, what happens by studying those things. They came up with methodologies for real parameters evolution algorithms. But fortunately, there are many ways the real parameter evolutionary algorithms have developed, and now we have a complete understanding, but the sources come from various fields and various ways of looking at it. So I'm going to talk to you about few, not of course everything, but few of those. So first I'll start with real parameter GA. Okay, real parameter GA. Here I'm trying to show you that binary coded GAs, when you apply to continuous search space, may not be very efficient. And the reasons is that we talked about schema. And I also talked about if you have schema that starts from the most significant bit in a contiguous manner, they represent a contiguous search space, subspace in the continuous space that you have, right? Like 1 and all star represents the right half. 0 and all star represents the left half. 1 all star represents the right quarter, the rightmost quarter. So it's all contiguous. And in a real parameter problem, that is a schema. That is a good building block. That is my optima lie in this space or not? But I also showed you a schema with star, 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 and 1. What does it represent? It represents only odd numbers. So it's a kind of fragmented region. It's not contiguous. Fragmented region it represents. Is that an important schema for continuous search space? It turns out no. Unless you have a periodic function, this schema is not that important. So you see that Holland's schemata concept, when you apply binary coded to real parameter, not all schemata are equally important. But he argues a very efficient schema processing process that happens in a GA for all schema. It doesn't differentiate. So since now in real parameter GA, not all schemata are important, that may not be an efficient search. So that's what I'm talking about here. Plus there is a Hamming cliff concept, which is if you take a 5-bit string and I have, let's say, one string that says 1 and all zeros, what it decodes to? 16. What this one decodes to? 15. So they are neighbor in the decoded space, or that means in the X space. They are neighbor. But is there any similarity between the two strings? Complete different. Every place is different. Totally complement. But so they are completely different, but in the decoded space which I am interested in, they are neighbors. So there is no continuity. There is no nice mapping between the string space and the X space. So these are called artificialities, artificial cliffs, and it's given by the name of Hamming. Hamming was a person who did a lot of contributions in computer science. Some people suggested gray coding is an option. It's a little complicated way to do coding. It's not the binary decoded value coding that I mentioned, but that's not also the solution. Certain neighbors decodes to neighbors, but not all neighbors decodes to neighbors. Okay, so it partially solves the problem, but not entirely. Other thing is arbitrary precision is not possible. As I said, the only way you can achieve arbitrary precision is by increasing the number of bits. Okay, one by one, and as I've told you, the population size becomes proportionate to the number of bits. So if you have more and more bits, you need more and more population size, which means your whole search will slow down. So we see that there are certain issues when you want to solve a real parameter problem with binary coded GA. So we want to avoid that and come up with direct way of doing it. So, oh, sorry, I had that. Okay. Now, why can't I move it? Yeah, now I can. Okay. So what is the issue if I'm directly dealing with variables that are real parameter? So that means I don't have any binary strings. You have told me 10 variables, x1, x2, all the way x10. Each one of them can take a real value. I can directly code those values, say 2.39, 5.89, like that. Okay, there is no binary coding now. So I have a vector like I have in the classical. Where do I have problem? Do I have problem with selection operator? First of all, go back. Do I have problem with evaluation? No. That's x already given to me. I can plug it in my f and constraint violation and evaluate and give a fitness. I could use our penalty parameterless constraint handling, right? Everything I can do, assign a fitness. Then next thing we are doing is selection. Do I have any issue with selection? No, because selection needs only fitness, doesn't require whether it's binary string or real or whatever. Crossover? No? Yes, because crossover we are doing on the string. Remember? 10 string, and here there is no string. So I need to come up with a new way to do crossover. Right? That's one place. Do I need to do anything on mutation? Yes, because there we are changing a 1 to a 0, 0 to a 1, but now I don't have 1 zeros. So I have numbers. I need to perturb it locally. So these are the two places really I need. Elite preservation, if I do extra, no. Again, whichever is the best as I copy. Instead of copying the string, I now copy the whole variable, vector, real parameter variable. So only two places you have to look at, recombination and mutation. If you can come up with a nice way of doing it, you will have your own real parameter GA. Okay, so that's the idea. So what do I do when I have one parent with n variable, these are all real numbers, another parent here, how do I get two new children? That's the part of the real parameter crossover. And when I have a real parameter mutation, I have a vector here, how do I create a new vector? Okay. Now with numbers, when you do some create, crossover is not the right word, because crossover means you are actually crossing things, right? So we don't call in real parameter GA that's a crossover, we actually call it a recombination. Okay, it's more of a blending that should take place between the two to create two. So if we think of very simple exchanges, like if you try to mimic the binary coded single point or 2 point. So if I have two variable x1, x2, and let's say this is my parent 1, 15.345 x1 value and x2 value 3.569, another parent here, I want to do a naive crossover like we've done in case of binary strings. So that means I'm going to choose one of these sites, okay, and I'm going to swap. Let's say I do a bit more efficiently, saying I'm going to choose one cross site for x1. So I've got 1, 2, 3, 4 positions. I will choose one at random and cross, and I will choose one more here and cross. So I'll do independently two variables. So let's say I have chosen, I think, here the first site. So I've got 11.142 and 25.345. Okay, and here I think I've chosen at the second site. So 3.587 and 5.669. It's a crossover. Is that an efficient one?
No.
Why not? You're right, it's not. Why not?
Population diversity going back to 11.
Yeah. Only if you do on the most significant bit, you have a big change. At the lowest significant bits, you are not changing too much. Actually, in binary strings, one bit to the other, there is a weighting effect of 2, a factor of 2. It gets more and more importance. Here, by a factor of 10. That's too much. Up to 2 we can tolerate, but anything more than that becomes too much change, positional dependence. Okay? When we are choosing cross site, we are doing it uniformly random, as if every cross site is important. But in this case, we should not do that. We should have a cross site dependency that reduces. Probability of choosing this cross site should be much less, maybe 10 times more less, compared to the choosing cross site over here. Then it will work, okay, if you do such a thing. Yeah.
So what if we adopt a different number system, suppose an octal number system or something? Like
yeah, you will be transiting towards decimal system, from binary to decimal. In the middle, you can do that, and maybe up to a certain point, you still get advantage.
So then the factor of this factor of 10 or 2.
Yeah, will reduce. Yeah. But the whole purpose is still lost because I didn't want to have any mapping in the first place. When I'm doing real coded GAs, I don't want to have any string or octal or hexadecimal, whatever mapping. No, I don't want to do that. I want to directly deal with real numbers.
Weighted average would help if you want to.
Weighted average of what?
Of the two.
Yeah, that would be another operator. Okay, that would be a new crossover. In fact, people have suggested that they call it intermediate crossover. Okay, yeah, but that's not again very efficient. We'll talk about why not. Okay, so this is not very good. If you try to get a frequency distribution of if you keep crossing at various places where the parents are coming, you will see that if these are the two parents you are doing, they are mostly surrounding here and here. Sometimes you can get over there and here. Okay, so it's not a very efficient way of doing it. There are two remedies to this. First is that we do variable by variable, but with much more sophisticated method that has some other properties. Like I said, if I had a reduced importance of site, but then how to reduce linearly or a more than linear manner is something that you have to come up with from somewhere. So I'm going to describe to you some ways we've come up with. So that's like called a variable-wise recombination in real parameter, or I can treat this together as one point. For example, if I have x1, x2, this is x1, this is x2, these 2 points actually represents maybe this point. So this is like a two-dimensional vector I'm representing, and this may be representing, I don't know, it may not be for this two or may not for this plot, but let's say I'm representing one parent here, another parent here as a point in my n-dimensional space. So there are 2 points. Now I do some vector operation in that space, and I create 2 new points. So this will be my new children. So you could do a vector-wise recombination, or you do a variable-wise recombination. First, we'll talk about variable-wise. Okay. So there are quite a few methods. The one that was first suggested was BLX, blending crossover. I'm going to briefly mention to you what that is. It has a parameter. Every one of them has a parameter called alpha, so that you have some control. Simulated binary is what we came up with. So I'm going to spend a bit more time on that. And then fuzzy recombination is another one very similar to SBX. Okay? But if you look at all these different methods, there is a common thread between them, and that's, I think, absolutely essential for you to have if you want to come up with your own, because this is an open field. You can come up with your own as well. And that's what I ask in my semester-long courses of this, is that the student should come up with a new method. Difference between the parents is used to create children. So if the difference so if parents are too far away, the children can be far away from parents. Okay? If parents are close by, children should not be far away from the parents. If you follow this principle, in fact, this is the one common theme about all these operators. But if you look at their papers, except ours, we kind of started thinking that way, but others didn't even mention that anywhere. But if you then go and look back why their method is successful, they have this property. Okay? All right. So let's look at the blend crossover first. Okay. So let's say that I've got a P1, P2. So I'm doing variable-wise now, right? So I may have a 10-variable problem, but I've chosen, let's say, variable. Okay, let me first explain to you how this works, because this will eventually come up. So let's say I've got 10 variable, n equal to 10. Okay. The way you apply this variable-wise is that you go variable by variable by variable with a probability of 0.5. Okay, so with 0.5 probability, you decide, are you going to blend this or not? Are you going to apply the crossover operator or not, or recombination operator or not? Okay, so if you have to, that means 50% of the variable will get crossed. That's the whole idea. And the 50% comes from the fact that if you do a binary coding crossover, binary strings, you do a crossover, no matter where your site falls, on an average, 50% of the bits get swapped. Because your site can be from the first one till the last one, anywhere in between. So on an average, it's 50% of the bit gets changed. So that same concept is followed here. This is, of course, our edition. Other people may not be using this concept, but this is how we systematize the whole thing. And in all our codes, this is what is followed. Is that with probability 0.5, we go variable by variable. We decide whether to cross a particular variable. If we have to cross, then we use blend or SBX or whatever. Okay? If we don't have to cross, we just keep it intact and move to the next variable. Clear? Yes, on an average. It could be 4, 6 as well, right? Before that, there is a crossover probability PC. When you got these two, right? When you got these two, first you have to decide with PC whether you need to cross or not. Like in the binary string. If this turns out yes, you have to cross, then you go in 50%, 50%. If right in the beginning you decided, no, I'm not going to cross this pair, you just take the whole thing and copy and do mutation on it. So there is a crossover probability check before even you come to this stage. Right. Exactly. So then if you have a crossover probability of 0.9, 90% of the pairs you'll be doing the cross, checking 50, 50%. 10% not even anything. Just take them and pass it on for mutation. Is that clear? Okay. Now what we are talking about is when your crossover probability has successful said that yes, we need to cross this, and your 50% probability is successful, let's say on this one, saying yes, I'm going to cross x2 and y2 now. And so give me two new numbers. So these are two numbers. Give me two new numbers. Then we are going to use these methods, right? So it should be absolutely clear what we are doing. So these are two new numbers, P1 and P2. No, two numbers from the parents, P1 and P2. It need not be that the first one has a lower value. It could be that this is the second parent and this is the first parent. I'm just naming first one to be P1 here, second one is P2 here in a generic manner. Here is the real line. Here is your lower bound and upper bound. Okay. And what you do in blend crossover is take a difference between P2 and P1 because these are real numbers now. You can take a difference between the two. Whatever is this difference, you multiply that difference by alpha, which is a parameter that you specify right in the beginning. And this parameter is kept fixed all along. Okay? Let's say a usual parameter value, or what they suggested to use, is 0.5. So alpha is 0.5. So you take the difference here, multiply it by 0.5 or alpha, and go that much beyond P1 on the smaller side and beyond P2 on the higher side. Is that clear? So I'm assuming P1 is smaller than P2 here. So I've got P2 minus P1, which is this difference, multiplied by alpha, and you go here on the left side of P1. So you get this point. Is that clear? And from here, you go the same amount, alpha times P2 minus P1 on that side, and get this point here. Okay, now you've got a big range from here to there, where P1, P2 is symmetrically placed, right? Now you go to the middle of it. You go to the middle of this. So P1 plus P2 by 2, middle of it. You create one number here at random, one number here at random. These are the two children. Okay. So you've got this entire range, right? You got the entire range. Okay. The original suggestion was you just create two numbers at random here. From here, this entire, you will not be creating anything from here and anything from there. Two number uniformly. So this is the uniform distribution, probability distribution. Any one of them is equally likely. Create a random number. Create another one there. So these are your two children. But we made it a little systematic. We say that first we said, okay, get to the half. So we want one children from the P1 side, one children from the child from the P2 side. Is that clear? So you can go to the middle of it, middle of P1 plus P2 by 2 right here, and then it divides into two halves. One you create here, another you create there. Later on, to be equivalent to our SBX operator, what we said, you just create one number at random here. One number at random, let's say it's somewhere here. Then you take a mirror image of that, you here. Okay, there is a reason for that, I will tell you. But this is our final suggestion. But the original developer, this was developed by some other people, and their suggestion was not that. Their suggestion was create 2 points uniformly from this entire range. Okay, so no property of both the two can be here, both of them can be here, both of them can be here, any possibility. That was their suggestions, but we made it a little systematic in order to, from the knowledge that we had from SPX, which I'm going to describe next, that becomes a much more systematic way of doing it. So you are giving importance to each parents and also keeping some properties. So is this clear, this BLX operator? Very simple, right? Now the choice of alpha is important, because if you have a small alpha, alpha can be 0, alpha cannot be negative. 0 means both of your parents are inside. Okay. Then as you start to increase from 0, you are going outside as well. And if you have too large an alpha, like alpha equal to 1 or alpha equal to 2, then you can go too much of a distance. Eventually you become a random search method. When alpha becomes so large that your entire space is covered, you are creating 2 points at random, it's a random search method. So you don't want to do too large an alpha to make it a random search. Okay. All right, so that's BLX, very simple to implement. So this was what was existing before we came up with SBX in 95. We were actually saying by that point, early 90s till early 90s, binary coded GIS were very successful. It was used to solve most problems of real parameter. So we assume binary coded GIS is very good. And the crossover operator is used there was single point or 2 points. So we said, okay, first let's take single point. And then we said, okay, we will look at it this way. What if these real numbers are coded in binary strings of some length? Okay. And we had applied a crossover, single point crossover. What kind of distribution of children we would have obtained in the real parameter? Let's study that first. So if binary coded single point crossover is important, if we study that, the distribution of children in the decoded space, because that's what I care about, then maybe I can directly use that distribution, not going to the binary string. So that's why, since it's motivated by the binary crossover operator, we called it simulated binary crossover, or SBX. Okay? So, but the whole idea is written here. And we did some theory and came up with some results which I'm going to show you, but 2 properties we observed for binary coded strings. Okay. It's not so obvious, but let's see what they are. Let us say I've got this string and that string, just one string to represent one variable. So here you've got 7 bits to represent a particular variable. Okay. If I decode that, it will be 85. So in the X space, if only I have is a decoded value, I don't map anything further, then this is my X value. And the second parent is another one. This is my map value. I take an average, and it's 68. Okay. These are 2 arbitrary strings. Now I choose a cross site at random anywhere here. This, let's say I've chosen this site, and I do a single point crossover. What's going to happen? This will get hooked up with this, and I get the first one. Oops. Yes. And this one hooked up with that, and I get the second one. Right? Everything is correct? Okay. Now I compute the decoded value. I get 83. I compute the decoded value, 53. I take an average. It's also 68. Matching with that. Is that a magic, or just happened in this case? Every time it will happen. You can prove it. It's very simple to prove mathematically. So that means, what is the implication? You are taking 2 parent strings when you cross. So parent strings you can map to some P1, P2. And what is the average? It's the midpoint between the P1 and P2, like I showed you here. It's the midpoint of P1 and P2. When you take the average of the 2, that's the midpoint. That remains preserved of the 2 children that you have created. The 2 children's average is also same as the 2 parents' average. That's why I do a mirror image. You see, I told you that I do a mirror image. So if I create one child here, if I take it over there as a mirror image, their average will be where? Right there. But if I do one child here and one child here, their average will be somewhere there, so that's not going to match. So if I'm following the success of single point crossover in binary coded strings, I want to preserve some of those properties, and this is one of the properties which we observe. So in order to do that, I modified the PLX so that one child you have the liberty to create anywhere around the first parent, the other one is automatic. Okay, is that clear? And we follow that in SBX as well. No, any crossover site you take. That's what I'm saying. You take any crossover here, any 2 strings, any crossover, this is always preserved. No, it will not be 68. But the average will be preserved. Yeah? That's what you're talking about. That's the first property. Second property we get from here is, what about if these two were my parents now, and I crossed it at the same place? What will I get back? If these two are my parents, these two children that I've got, if they were my parents now, and I crossed it at the same place, what would be my children? Get back the parents. Which means I've got two pairs, P1, P2, and I've created two children. If I cross these two children, I should get back the same parent if at the same event, same place if I had crossed. So that means the probability of creating 2 points as a children from two parents is same as probability of creating the children from the two children, right? So all this you have to keep in mind when you are following such an operator. Okay. So we put this as constraints in our developmental process. I'm not again going through the whole 3-page calculations, but the paper is there if you want to look, if you want to read it and see how we have come up with. But to do that, I needed to have some non-dimensionalized parameters, because now I can get two strings or two real numbers to cross. Next time I may have another real number, so I cannot have a crossover that is specific to that particular pair. I need to have a very generic method. So what we came up with was a parameter called beta, which is defined this way. It's an absolute value, so it cannot be negative. Okay? The difference between the two children that you have created divided by the difference between two parents that you have. Okay. And the property that P1 plus P2 is equal to C1 plus C2. Okay, that comes from this observation here. So if I tell you that, now let's say I tell you I've got a crossover, I can represent a crossover event with just some specific value of beta. Let's say I say beta equal to 0. What does it mean? With these two properties that I just talked about and this definition, if beta equal to 0 means where are the children? What is identical? The two children are identical. Everybody agrees? So the difference between C1 and C2 should be 0, which means C1 is equal to C2. So where is the location of C1 and C2 now? By 2. Because their average of the two children should be same as the average of the parents. And if the two children have no difference, where they should be right at the midpoint of P1, P2. So if you are creating two children that are identical, the only way you can do that is when these two children are at the average of the two parents. That's also a crossover, and that's defined by just one number. That's beta equal to 0. We'll achieve that every time. It doesn't matter which two parents you are taking, which two numbers you're taking. As soon as you say beta equal to 0, I know what you're talking about, where the children are. Is that clear? What about beta equal to 1? Now I go from, because it cannot be negative beta. So 0 is the minimum. Now I'm going to, let's say, 1. What happens when beta equal to 1? No crossover. Parents are same as children. Everybody seeing that, or only one or two people? These are simple math, right? Just spend a little time thinking. Parents, so I don't know whether C1 is equal to P1 or C1 equal to P2, but their difference is the same. We can decide that later, which is going to go where. But the two children are identical to the two parents that we had. So when you go from, now let's go back to my point here. So I said when beta equal to 0, we are right here. Two children are right there, right, at the midpoint. Beta equal to 1, the children are now moving as you go from 0 to 1. Both children are getting separated now, and both of them are moving symmetrically. Eventually, when beta equal to 1, it's reaching P1 and P2. So naturally, when beta greater than 1, we'll be moving out, right? So let's see if that's happening. What is beta equal to 2? So greater than 1. So now the difference between the two children is twice the difference between two parents. So in this case, they will be for alpha equal to 0.5, because now you have this distance will be twice this difference. So two children are here and there. Now I can go beta equal to 3, then I will be here and here, right? I can keep on increasing beta, and I can go, my children can go away from it. So you see now that just by controlling beta, I can actually tell you where my children are, provided you gave me P1 and P2. Now it could be any two P1, P2. I can have the same distribution on beta, and I can pinpoint where your children are, right? So if I can come up with now, is each beta equilikely? So beta I know goes from 0 to infinity. It can be infinity also. 0 to a very large value. 1 means you are right on the parents, then you are going out. Now, obviously, I don't want to have beta with uniform distribution, that any beta is likely. So what is the distribution of beta? If I can come up with, then I have a crossover operator, right? Okay. So that's where we've done some math. So beta less than 1 is your children are inside the parents, right? In between the parents. We call this a contracting crossover, because your children will have a contracting space than the parent had. Beta equal to 1 means stationary, you stayed where you are. Beta should be greater than 1. Then you are expanding. Please change that. Beta greater than 1. Expanding, you are moving away. And the second property that I said, that when you cross children at the same place, you get the parents back, says that for each contracting crossover, for each beta, so if beta is 0.5, I'm now thinking of a probability of beta, right? How frequently, what beta I should use. If I choose a particular, let's say beta 1, which is less than 1, I should have an equal probability for an expanding crossover with 1 by beta 1, because then 1 by beta 1 will be greater than 1. And that is the thing simulating that when you cross the children, you get to the parent with the same probability. Okay. So with all these properties put in, there are two things I did. First, I did theory, where I'm showing you here the results for a particular case, where I've got all 0 strings and all 1 strings, and I actually do a math with this. This is the distribution in beta that comes out. So you see, this is beta here. 0, there is a small probability, but as you are going from 0 to 1, your probability of doing crossover, probability of creating those as children is increasing. So this is actually coming from theory, okay, where I have 2 particular strings and I have actually crossed it at various places, and the theory tells me what should be the probability. And you see, at 1, the probability is high, whether you are coming from the contracting side or from the expanding side. So that actually says 1 means the same as the children, parents, right? Children same as the parents. That says that you should have higher and higher probability of creating children near parents, either from the lower side or from the higher side. You should create with a large probability. As you go away from the parent, the probability of creating that as a child should drop. And it also makes sense, right? Because if these 2 parents you are crossing, you don't want to create a children far away. The probability of creating children around them should be higher. And that's what it says. And then we actually did an experiment with 15-bit strings. With 15-bit strings, how many strings you would have? 2 to the 15. And that's a huge number, right? And we take all pairs of those. So you can imagine how many crossover we had. And for each pair, we have 14 sides, because there are 15 bits, 14 different sides. We do a single point. And every crossover we have, I get a corresponding beta. I create 2 children, I calculate beta, and I have a frequency distribution on beta. This is what it looks like. So it says that now here it's 0. At the midpoint, it's never creating anything. And then at 1, it has the highest probability. And then as you are getting towards 1, going away from 1, getting towards 1, probability increases, going away, probability reduces. So you see the similarity, my theory and the experiments, it matches quite well. So I'm totally convinced that if I do a binary coding, and later on we have confirmed for 2-point crossover as well, it's very similar performances come out, is that if I define the parameter beta and draw a frequency distribution of what beta should be more likely to be created as a children event, it turns out near parent you should have more probability, and as you go away from parent it should reduce in other direction. Okay. So now these are complicated functions. This one I cannot even, there is no mathematical function. Here I have a mathematical function which looks like this, but I came up with a very simple polynomial function to describe this. So I actually defined a polynomial function which is this. By the way, another thing I observe is the probability inside this and probability inside this is exactly the same, and that's this children crossing gets the parent with the same probability comes in. So probability of making a contracting crossover is identical to the probability of making an expanding crossover, and the stationary one you can put 50% this way and 50% that way, okay, if you think it that way. So you have equal probability. So all these, this one that we came up with, a polynomial operator on beta, ensures all that, and the corresponding expanding. So the crossover probability curve, when you say beta and eta, so this is eta, here is, this is a control parameter that I have, and this is supposed to be eta, but it looks like an n, but it's eta. So when eta equal to 2, this is the distribution on the contracting side on beta. It's a quadratic curve, and this one gets derived this way. So this is 1 over beta to the 4, and that falls up like that. And if you now calculate the probability under the curve from 1 to infinity and 0 to 1, they are identical. 50% probability to be inside the two parents, 50% outside. You can do this for any eta. If you choose eta equal to 0, you get uniform between the two parents, and then it drops as you go away. So it's like BLX, but BLX doesn't have the going away thing. It just does it in between. And then as you increase eta, you get more picky distribution. So you are actually not going away from the parents too much if you increase your eta. But so the idea is, if you don't want to go too far away from the parents R, then you should use a very large eta. And if you want to create points a bit away from where the parents are, then you should use low. So based on lots of computations, we figured eta about 2 is a good number for single objective optimization. When you go to multi-objective, you got to be more careful, and then we use eta starting from 10 onwards. Then it starts to work around that point. Okay. All right. This is a very important slide. All this is theory. All this is to motivate you how all these have come by following the binary coded crossover. But if you have to implement this, it's very simple. You create a random number between 0 and 1. Compute this quantity beta q that comes from this polynomial distribution that I have talked to, the distribution. It depends on you, that you have random number you've created, and eta c you have chosen. Now, to differentiate from mutation, we call it not just eta, but eta sub c. Okay, so it's to say crossover. And this is the parameter I said you can choose 2 for single objective optimization, and you keep it fixed all along. Okay, so this is how you create beta q that actually does this nonlinear distribution, and then you create first child from p1, p2 by this formula, second child by this formula. That's it. So if you don't want to understand the theory, it's fine. You can just use this. You still have the whole idea working. Okay, and so if you look at our code, this is what's implemented. Okay, the effect of this is this. Let's say I've got two real numbers, 2 and 5, 2.0 and 5.0. You want to cross now. You want to have two new children created. So is it going to be 1.5 and 5.5 or something else? You need to decide. How do you do now? Okay, the distribution is this. Okay, the way we do is here. But if you choose different random numbers, this is the distribution you're going to get. This is taken from the polynomial distribution. And now that was in the beta space. Remember, this is in the beta space. Okay. Now if I translate this into the x space, you get this bimodal distribution. Okay. This one is very much like the beta distribution. Okay. So at the midpoint, you have 0 probability of creating a child. So if you have 2 and 5, so 2 plus 5, 7 by 2, 3.5 has a 0 probability to be created as a child. But slightly left or right of that is okay. There is a probability. And then there is a finite probability as you go away. As you are coming towards 2 and as you're going towards 4, the probability increases to its maximum. And then when you cross 5 and cross 2 on the negative side, your probability reduces down to 0 eventually. Okay. Now this is with eta is equal to 2. If you had chosen eta is equal to 5, the distribution would have looked like the dashed line. Now you see, if you're thinking, okay, I've got two parents, 2 and 5. If I use 2 as eta c, what is the probability that 1 will be chosen as a child out of crossing 2 and 5? There is a finite probability, and you can see there is a good probability, right? About 0.1, slightly less than 0.1. But if you now increase eta c to 5, it has almost half the probability to be created as a child. So now you are creating more and more points close to 2 and close to 5. So that's the effect of eta c. Okay? But still, this distribution is governed by the difference between the two. You see, p2 minus p1 will come in both these. The difference is very important, and I'm going to show you next that effect. Now I'm fixing eta. Okay, I told you use eta equal to 2. Okay, so you fix that eta. This is for eta equal to 2. Now let's say early on, I'm running my GA. My points are all over the search space. So I've got, let's say, 2 points that are far away from each other. Like in this case, far away means, let's say, 2 and 5. And I apply these SBX. This is the distribution. And I want to compute what is the probability that 1 will become now an offspring of 2 and 5 with eta equal to 2. Eta is fixed now. But my parents are at 2 and 5. There is a probability, I told you, it's about 0.08 or something. probability. So it's a small probability, but it's there. Now let's say later on I don't have 2 and 5 in my population. They have, that variable has converged very nicely. By the action of selection crossover, you've gone close to the optima. Now your points are close to each other, and you have this kind of situation. The 2 points that you are crossing is 2 and 2.5, not 2 and 5, but 2 and 2. They're very close. I'm still using eta c equal to 2. How does the distribution looks like? Now like this. So it's the same probability distribution, now depends on where the 2 parents are. Okay? It's automatic, this dependency. And now the distribution looks like this. Now I'm asking the same question again. What is the probability of creating 1 as a child from 2 and 2.5? So what your guess is? It should be very small, because when you say 2 and 2.5, you're talking about that region. 1 is far away from where the parents are. But when you have 2 parents which are 2 and 5, 1 is not far away. It's a relative thing, right? This way that we have defined beta and defined the operator, it takes care of it. Okay, you don't have to do anything extra. All you have to set is a eta value. That's it. Either it's 2 or 5. If you choose eta equal to 2, you have this effect. So this probability may be 0.001. You can't see it with naked eye, but maybe there is a small probability because it goes to infinity here, minus infinity here. So 0.001, let's say. Now, if you only use eta equal to 5, this should have gone down even further. Let's say 0.001, 0001 maybe. And this one would have gone down a little further as well. Okay? So you can control that overall thing with the choosing an eta, but after you have chosen eta, this kind of population control that your children is now dependent on how the population diversity is automatic. Is that clear? So it has the self-adaptive property. As if your population is diverse, this is helping you to create diverse children. And initially that's very helpful. Initially you're looking for where to converge. You don't want really convergence in the beginning. You want to search the whole space. After you've done that and converge in a nice area, converging in the nice area, this one helps you to converge even further, because now it's not going to take you out from there. It's allowing you to do a more precise search right there where it is. So it has both the aspects that's needed, early on, intermediate, later on, whatever is needed, it's there. And you doing anything else. And you are not doing anything there for it to work. Okay? So only parameter is eta c. And I'm suggesting you to use 2 for single variable. In most problems we have done, that gives us very good results. Okay? Here are some results just to show you it's a very simple function, single variable, x minus 0.5 absolute. So it has a kind of this kind of a function where at 0.5 it's the optima. The function value is 0. And search space is between 0 and 1. First, what I did is I did a single point binary crossover. 50 point is created in the range 0 to 1. We have used 30 bits to get good precision. Our termination criteria is a little harsh on this. I said that we need to get 1 point between 0.5 plus minus 10 to the power minus 6. So 0.5 plus minus 10 to the power minus 6, if you get, we will terminate. We'll say it's a success. Otherwise, we say it's a unsuccess. So binary coded GA, because of the string representation, 23 out of 100 runs, it was successful. It couldn't get to that precision, but it came very close, but not to that precision. This is one of the issues with the binary coding applied to real number that I told you about. And on an average, those that are successful could run with 835 function evaluations needed. So many function evaluations needed to get there. We now try SBX, range 0 to 1, 50 population size. We use different eta c, 0, 2, and 5. Every time it's 100% times it works. And function evaluations is best for 2, 740, 749, let's say 750, compared to even binary, compared to even other eta c's. Some of these studies have convinced us we should use eta equal to 2. Okay? Increase the population size is the same effect. Okay? Maybe eta c changes to some other place now, but 2 is a good number. When we tried BLX 0.5, same thing, 50 population size, also 100%. But it needs, well, comparable here, okay, and comparable over here. So this seems to be saying that BLX 0.5 may be better for this single variable problem when you have 0 to 1. I wanted to see the difference really, where the difference lies. So next what I did is we initialized our population between 0.9 to 1 in one side of the search space. Here is my search space with 0.5 here, but now I've initialized at 0.9 to 1 all our 50 members. Okay, 0.9 to 1. So the algorithm has to now move out from there and come to 0.5, because every points were between 0.9 to 1. It took little more evaluations, but 100% of the time it works. Now BLX is start to show its weakness. Okay, at that biased initialization, okay, it only works 24% of the time. When you did even further, 0.99991 means if I show you all the points, they are just on one point, all the 50 points. Now it has to go out from it and get, it takes a bit more evaluations because it has to go out and then go to the right place. But SBX does 100% of the time. Now BLX doesn't work at all. Okay, so it's too much loss of diversity. It cannot just fan out to all there. So there are. So if you look at all these different situations, SBX comes out to be a winner. And then we tried this on not only such simple problems, but difficult problems, having multimodalities and all that. Again, I mean, good performances compared to single point. Okay. Now, we said that the SBX that I just mentioned to you goes to -infinity and +infinity. It can create a point far away from it. But what if you have bounds? You have a variable that says, oh, you cannot go beyond lower bound and upper bound. So, but your SBX doesn't know that because we have not incorporated that. So you can create a point here. You see, there's a large probability of creating points here. So what do? You modify the SBX operator where from this bound on, because the probabilities are very simple polynomial functions, so we could do probability calculations easily. We actually compute the cumulative probability from -infinity to here, to the lower bound, find this probability, and this one is redistributed here. You see this? This was the original, the solid, the dashed one is the modified. So that there is 0 probability here, and all the probabilities are here to create. So this probability is 1, completely probability 1. You will create one child here. And similarly, this one is computed and redistributed here, and you get here. Now, with this modified one, you will not go beyond your bounds. You will be always satisfying the bounds, and still has that BLX property, SBX property. We then became a little more adventurous and said, why not? This was developed for real coded, but we could actually also apply it to discrete variable problems. Only thing is, we will use a discrete probability distribution instead of a continuous. So the silhouette of that is this kind of binary SBX operator that we have. So all these are integers, and 0.5s are allowed. If I have to apply this between 5 and 10 or 2 parents, any of these numbers that you see with the line is allowed, and their probabilities of creating as a child is shown here. So you will be creating 6, 4, 4.5, 5.5 with a large probability, and similarly near parents here large probability, and as you go away from them on either direction, your probability reduces. So you can also apply this for discrete variable spaces. Okay, we then did an equivalence of different operators. So here is SBX, BLX. I haven't talked about FR, but that's another way of doing it. If you choose eta equal to 2, that's as good as choosing alpha equal to 0.662, not 0.5. And D values for FR is 1.0. So we, based on some theory, we came up with some of these equivalences. So if you don't like SBX, you can use BLX, but then use 0.662 if you were to use SBX equal to 2. And you can also map it this way. 0.5 means going up to 3. Okay, what about mutation? Again, you need to change the mutation operator from bit flipping to something on real numbers. One naive way they suggest is, well, if this is your number you want to mutate, go to its lower bound and upper bound, create a point uniformly at random. I will never suggest you to do that because this is a random search. So don't do that. But I have seen people using it. It's simple-minded. You are not relying on your algorithm. You don't trust your algorithm when you're doing this. Okay. So you need to have more biased way. If this is your parent, you want to create children around it, not any point uniformly in the entire space. Then you're doing a random search. This is that. This next one here is a Gaussian distribution, and a lot of people use that. So you have your point here. Keep this as the mean, and use a Gaussian distribution. Now, only thing you have to specify is what is the standard deviation. That's a problem. But if you can specify a standard standard deviation, you can create points around it. Now, the evolution strategy people do a whole lot of work in trying to come up with how to set the standard deviation. So they spend their whole research efforts in trying to come up with that. But that's a very important parameter. We came up with an extension of SBX in a similar way, like we have eta c, we have a polynomial mutation operator that looks like this. So this is your parent point, and you go down to your lower bound and go down to your upper bound from there, so that the probabilities here is 0.5 and probabilities here is 0.5. So you can be either way. If you create a random number, if your random number is greater than 0.5, you'll be creating here. Less than 0.5, you'll be creating here, but not with uniform. With probabilities are more for near parent. There is a discontinuity here because you may be biased towards one of the bounds, so you cannot use the same probability. Okay? But these are very simple probabilities with polynomial that we have coded. A description of this you will find in the literature, in my book and other papers. Okay? Okay. This kind of framework now with the SBX and polynomial mutation, we have a real coded GA and we have a binary coded GA, is really very ideal for you to now put them in a combination to solve mixed integer programming problem. So let's say I've got an engineering design problem. Some of you in mechanical and civil would know this, is that if you have a beam or a bar or whatever you have here, first thing you want to, so you can be very flexible now. So you haven't decided whether you are going to do a circular cross section or a square cross section. You haven't decided yet. So that's one of your variables. So how many solutions you're talking about? 2. Either circle or square. How many bits do you need to represent this? These 2 options. Just 1 bit. If that is 0, it's a circle. If this is 1, it's a square. So with 2 options, bits are idle. So I need just 1 bit to represent what is my shape. Okay. Then once it is circle, I need to know what is diameter. That could be my another variable. And that I'm saying diameters are not available in any sizes. So this could be discrete. So this parameter can be. Similarly, if I say this is area, they may not be available in all sizes. So it could be discrete. So this variable d or the side length can be the next variable, which could be an integer or a discrete variable at the steps of 0.5, for example. The length here can be another variable, how long it's going to be. And that could be, let's say, I can assume it to be a continuous variable up to 3, 4, 5 decimal places I can cut it. Or you may want to call it also discrete if you want. But let's say if it's 3 decimal, 4 decimal, I might as well call it real. Okay? So let's say for our conversation's sake that I make this as real. Okay? So that I can have real, continuous, real, discrete, and Boolean options. Next one is very interesting. I talked to you about materials, right, in the classical way, and I said that you have to code it 1, 2, 3, 4, and there is nothing like 2.3 as a material. We avoid this here by saying, okay, here is my list of 8 materials, and I'm going to put now a coding. 000 is steel, 001 is steel number 2, and 101 is aluminum, and so on and so forth. So every code here has a corresponding material with its properties, Young's modulus, and strength, and Poisson's ratio, whatever I need, everything I know about it. And my coding is my variable. So this is what Professor Das mentioned in the beginning about non-numeric. So this is a non-numeric kind of variable that I can also add to my string here. So if I have now one string in my population that will look like this, a 1 and a discrete number, and a real number and a coding, 3-bit coding, then this says that I'm talking of a beam which is square cross-section, having a side length of 14 in some unit, let's say 14 centimeter, having a length of, could be 23.457 meter, if I'm doing a meter there, and it's made out of aluminum. So I've also included material as an option, as a variable. If you want more features of the solution like tapering, then you say what is the taper angle, you can add it here. And if that comes only 2 or 3 options, you could do that. If it can be a real number, you can do that. So you can keep on adding features, and you can keep adding them over here. There is no bias, there is no restriction. They all have to be integer, all have to be real. You can have anything. Even Boolean option is included. Ternary option can be included. You can just do anything. So it's a very flexible way you can represent your design. It's just a matter of now you're thinking and sitting and deciding, am I going to keep all of them as variables? Or I'm going to fix to certain things so that I don't unnecessarily increase my number of variables. But this platform allows you to put that. So this whole thing I published in an ASME journal, and I gave this a name called Genius, Genetic Adaptive Search. Okay, but we have followed these things to solve many industrial problems with, and also practical problems taken from the literature where they were not solved using this way. If you have to use a classical method which cannot handle discrete variable well, how will you solve this problem? Well, first you are going to say, I'm going to fix it to circle. Okay, so this is not a variable anymore, you fixed it. Then you say, I'm going to choose material number 1. So still 1, circle, I have 2 variables, diameter and length. Let's optimize, get a result, store it. Then you say, I'm going to change the next material, optimize again, next material, optimize again. So you do 8 times. Then you change this to square, do 8 more times. So all the discrete you are doing one at a time, or you go to branch and bound. Now I told you this one you cannot do branch and bound, because first thing in branch and bound is you have to assume this is a real number. What is the real number? I don't know. Similarly here you have to assume this is a real number. What is 0.5? What shape is 0.5? I don't know. So you cannot simply do. The only way to do using classical methods is do it one at a time, all these combinations. So too many optimizations. But here I'm doing all together. All my populations are mixed. Some members are saying circular, some members are saying square, some members have this material and that material. Okay, so it's a very flexible environment that you can apply these operators are. By the way, if I'm doing this, what would be my operators? So evaluation is fine. I can find the fitness or it's feasible or not. With one bit, I cannot do crossover. So only thing I have to do is mutation on this bit. This one I could do SBX because this is a real number now. I'm sorry, not SBX. I could do the discrete version of SBX. Okay. This one I can do SBX. This one I can do a 1-point crossover because there are 2 sides. Right. So, and then your another parent will also have a similar structure. I am never crossing this variable with that variable. Have you realized that? Because one of the students, when I was describing early on, asked me, sir, how can you cross this with this? But I said, you never have to, because you have a parent here which also has a similar structure, and you are doing variable by variable crossover. So this one you are crossing with another 3-bit string. You are never crossing with 23.457 like real number. This one you will be crossing with another such real number. Then you could do a SBX. This one you will be crossing with another discrete variable. Then you can use this kind, like I showed you, this kind, crossover, right? So you're always doing crossover between similar type of variables. You're never mixing up. So the whole things work. Okay, now I'm going to talk about the vector-wise. Vector-wise means we are not doing variable by variable. That 0.5 business I told you about is not there anymore. You decide whether to cross these two, and then straight away do the crossover if you have to do. There are lots of methods. I'm going to talk to you about one, and then because I need to move further. So the way, and this is again what we came up with called parent-centric crossover. So what we do here are PCX, kind of following up from SBX. Okay, you need 3 parents to start with in any dimension. You need 3 parents. So parent 1, parent 2, parent 3, and we suggest that you compute whichever is the best in terms of function value and or constraint violation, whatever. If all 3 are infeasible, you have to take the one with the least constraint violated one. If all 3 are feasible, you take the best feasible value. And if some of them are feasible, some of them are infeasible, you take the best feasible one. Okay. Let's say that's the number 1. So that's called the index parent. So we always create children around that best parent. Okay. Now how do we create children? With the ellipsoidal probability distribution. That has we need 2 numbers. One is the major axis idea, and this is the minor axis idea. So the major axis comes this way. You take the centroid of the 3 parents, compute the centroid, because these are all vectors, right? You can compute the centroid. And then compute the distance from the centroid to the index parent, this d. So the major axis here is in proportion to d. If d is large, your ellipse will be elongated like that. Okay. And then what you do, this line you extend, joining the center and this line you extend, and drop perpendiculars from the other two parents onto that line. So you'll get two numbers, take an average. So this kind of gives you an idea where your other parents are compared to this line. From this line, where the other two parents are on an average. If this is large, then they are far away. If this is small, means they are close by. So the minor axis is in proportion to the average of D2 and D3. Okay? So now you see, if these 2 points were very close to the line here, that means you have three parents which are really in an elongated manner, they are lying. This thing, the ellipsoidal distribution is going to be more elongated, right? So you will be going in the direction of the best from these two parents. So your children are following that distribution of the parents. On the other hand, if they are like a perfect triangle, like a regular triangle, right, then it's almost like a uniform distribution that you are going to have around the index parent. So the other two and this index one together is talking to you about how the search space is, what search space you are going through. Does it have to be really squeezed that way in order to get to a better space? Or it's a nice search space like a quadratic function that you can do uniform. So it kind of gives you that idea. And you see, all our children are kind of around the best parent. That's why we call it parent-centric. Parents is at the center of the distribution. SPX is also like that. The children are around the parents. It's all parent-centric. And there's a reason for that I followed right from the beginning. Why is that? Because the parents have passed through the selection test. Parents were compared against at least another population member and found to be better. So I can create children around it because they are better than at least something. Now if you come and say I'm going to do a mean-centric, so this one, there are operators, maybe I have it next, yeah. So this is PCX. If you apply it on all the three, I'm showing how the distribution will look like of children. This is another one called UNDX, proposed by some Japanese researchers some years ago. So if this is 1, 2, 3 parents, this first thing you do, go to the centroid. Okay, so centroid is right here, and make a distribution of very similar to what we are doing around that. So now mean is in the center of your creation of children. Why is that not a good idea? That's because your parents are good because they compared with another individual at least and found to be good, but not the parent. You've never compared parent with anything. Sorry, the mean. You've never compared the mean with anything. And you're trying to put all your children there where you've not even computed, you're taking a risk. Right? Particularly in the beginning, when your parents are far away, they may be individually good locations, but when you go to the mean, you don't know how that location is. Later on, this may be useful. So I think a switch from PCX to UNDX as we go with generations is a very good idea, which we have done later on and showed much better performance. Is that clear? The difference between mean-centric and parent-centric and when we should do when, what? Yeah. Okay, I'm going to skip now some of these things. Okay, these are more generic descriptions. Come to differential evolution. Okay, so this is another way of doing evolutionary algorithm, but not with the GA concept. Okay, not with the GA concept of crossover, selection, then crossover that followed with mutation. Okay, that's really the GA's proprietary steps. Differential evolution does it in a combined manner, but they gave it a different name. This also came out around 95 when my SBX came out. Okay, so let's first describe the method. So we move to some slides. You can just see where that is. Page number 80. Yes, page number 80. Let's go to that. Here you need first 3 points. Okay, so x1, x2, x3 you randomly choose from your population. Okay, and you call them, one of them x1, the other x2, the other x3. These are vectors. Now we're talking about the whole vector here. What you do is do this operation. That means take the difference vector between x2 and x3. Okay, so for example, in the sketch I'm showing you, if this is x2 point, that is x3 point, the difference vector is this, x2 minus x3. Multiply this vector by a parameter called lambda, which you have to set beforehand. Usually 0.9, 0.8, less than 1 is used. Okay, so let's say 0.8. So I multiply this by 0.8, means I have reduced it 80% of its length. So it will be smaller length. Take that vector and add to x1. So take it and add it to x1 and you get this new point called v. Is that clear? So 3 of the parents were involved to get v. Now what you do is you choose your best parent of the population. This is one of the D. The D has several versions, but this is most popularly used. Xik is the best one of your current population. Okay? Or it can be another one if you're following another version of D. Okay. So now that you have that and V, it's a vector. Let's say it has 10 variables. This is a vector. You just compute it as 10 variables. Now you go variable by variable by variable and take one from V with the probability P. And if this probability doesn't turn out true, then you take from the best parent. This is another parameter. So you have to supply P and lambda to have this operator working. Is that right? Xik is the best individual of the population. This is the ith variable. I'm saying it's the kth point, but it actually k could be the best, or k could be the fourth point, any other point, or you can use some other scheme. This better be a good solution from your population in order for it to be a good algorithm. So the best thing you could do is choose that as the best solution so far. Whatever is the best solution you had so far, that's that. That's the Xik. Is that clear? Or any doubt? Okay. So what is happening here? Let's try to understand. Again, the difference between the two vectors is used. If your parents are, so x1, x2, x3, xk, all these are your parent members, right? If they are widely separated in the whole search space, all these differences are going to be large. Then you multiply it by 0.8 and you add, you get a V also far away from the parents are. And then you are taking some from V, some variables from Xik. So it could be one of these two or these two in case of two variables, but in higher number dimensions, you are taking some of the variables from this one, V, and some of the variables from your best, and you are calling that as your child, one child. Okay? So it's a mix. So they call this part as crossover, simply because you crossed few variables. You've taken some from this and some from the best and some from this created child. And these operations they call the mutation operator. Okay, with our nomenclature, do you agree with this? Also, it doesn't matter. Your algorithm performance is not going to change what you call it. But to be terminologically correct, I mean, is this a mutation operator?
This is more of a crossover thing.
Yeah, it's more of a recombination because three parents are involved. And remember, mutation, according to biological definition, is just perturbation of one of evolving. So this to me is also a recombination. And this is also a recombination. This is more like a crossover because you are taking some from, it's like the uniform crossover. Like I said, if P is 0.5, it's a uniform crossover. But they don't use P 0.5. Now, if you use P 0.1 or 0.2, less than 0.5, you are giving more stress to keep variables from the best one. So if you want to have your algorithm more greedy, that means you are solving a unimodal problem with just one optima. You should make P very small so that your best is given more in importance. If you are dealing with a multimodal problem, then you don't want to just cling with the current best because you want to get better and better. So you want to do with P maybe greater than 0.5. Okay, so depending on the problem, you may have to choose these different values.
So can we change P with steps?
You can change P and lambda with steps. All these are, they usually keep it fixed, but you can change it. But then you need more knowledge how you're going to change it.
So like towards the
all
end
that.
when it's converging, if we
You want to make it less and less P. Yes, I agree. So you need to maybe start with a large P and go on reducing down to very close to 0. And lambda you may want to keep fixed because it has already the self-adaptive property. But this is the algorithm. Then what happens? What happens with the child? Y vector? You just enter into the population. So it's a one child created and enters the population. In order for it to enter the population, you have to delete something. So you can either delete the worst parent, worst of the 4 parents. I mean, this is of course the best. So of the 3 here, x1, x2, x3, you can delete the worst one. Or you can just delete the worst population member. It's not just worst of the 3, but the worst of the whole population. Or you can take one at random and just delete it with this new mutated point. Various things you could do, and they have various versions based on what you're doing here. And then you start again. Again, you pick 3 at random and then continue doing that. Now, this is called a steady state evolutionary algorithm, where you are not waiting till all n offspring population members are created, and then you combine with the parent, keep the better one. You're not doing that way. Every child is created one at a time, and then it has the chance to enter the population and can become a parent immediately. Because next iteration, you can choose this as one of the parents. But in GA, you don't have that option. But GA also has a steady state version. You could also do any of the GAs I talked about the steady state manner. One child at a time or two children at a time you create by SBX, and you can enter them into the population. And then shuffle it and again do selection and choose two. So if your child is good, the advantage of the steady state is if you've created a good child, it can immediately become a parent and start contributing in creating better ones. So you have a much faster convergence this way, but you can become also very greedy with this. So a mix between a complete steady state, point by point, one by one, versus the whole population is a good idea. Maybe you wait till 20% or 25% of your children or population members are created as children, and now you can enter them. That may be a better idea. So all these you see are very flexible algorithmically. You can change one operator. You can change the algorithm that goes with the operator. It's all in your hand. Okay? And that's what people have been doing before they release a paper. They do all these studies to figure out what is the best combination for this class of problems. And so it requires some research. And you can get a master's thesis with that. A PhD, you need much more work. But there should be some theory that says why this is good and all that. But it provides a nice platform for you to just think a little bit innovative and see what are the things you could do, why you should do this way, that way, and then continue with it. There are a bit of motivations that, modifications that come with these different ways of doing it. I said different versions, but let's not go into that. Let's not also show the results here. I'm going to quickly talk about PSO, and then maybe tomorrow I'll just finish up if I'm left with anything. It's another real parameter GA. Oh, by the way, they don't call, the PSO people do not recognize this as GA. They don't call it a genetic algorithm. They don't even call it an evolutionary algorithm. It's just in the name. So it's a population-based, nature-inspired algorithm. Let's put it that way. Okay? It actually follows how the swarm fly, like birds or a school of fishes. They swim. There is a lot of coordination that happens, right? So they tried to, Kennedy and Everhart again in 95. This was a pretty good year, actually. A lot of new ideas came out around that time. They were trying to get this idea from what principles the birds use to fly. So first question to ask, are they optimizing anything when they're flying? First of all, you have to, when you mimic some natural events, you need to first convince yourself, I'm trying to solve optimization problems and I'm trying to follow something from nature. Is that event that nature is doing is trying to optimize anything or not? In almost all cases, the answer is yes, because it's trying to do it in a better and better way. When better becomes best, you're optimizing, right? But better means still you're going towards optimal solutions, because when you compare two things, you choose the better one, means you are in that process of getting to the optima. And nature always does that, because nature is very thrifty. It doesn't want to really unnecessarily do something. Okay? If it's not needed, it's going to find out, and eventually you'll have a better solution. So yes, I mean, it is trying to optimize maybe the efforts. All the birds that are at the edge, they get the whole blunt, and those who are inside enjoy the ride. But then they are not that harsh that always the same birds at the edge are at the edge. They switch places. Okay, once they get tired, they provide some kind of indication, and they come in. The one close to it goes there. So this whole effort of going in a pattern, as you see, all these are to minimize the effort of doing something. So there is a concept of optimization. All right. So there are three parts in the whole effort of how do you do it mathematically. How do you update the location of current points to the next point? So the location of each bird. So each bird is a population member in a PSO. It has a location. So in a bird situation or a fish situation, you only have 3 dimensions. Okay, x1, x2, x3, you can fix it, and every bird you can locate. But you can use that concept to do higher dimensional problem solving as well, and that's what they are doing here. They are generalizing it. Location of every bird, ith bird is xi, it's a vector. It gets updated with a velocity, they call it. So from the current location to the next generation location would be that you add a velocity component to current step, to go to the next step. Velocity has three parts. First thing, its own velocity. That means from the previous iteration, time step, so iteration here means the time step, to current time step, how did you come? What is the vector by which you have come from previous to this? So that's your VI. That's your VI. Okay. Then there is one component that says that bird's location from the beginning they started to fly till this point, that means initial generation to current generation, what location along the way had the best fitness of that individual. So here in PSO, every individual has a trait, has a mark that says first population member of current generation, first population member of the second of the previous generation and previous generation, all are linked. This is talking with the same bird. Second population member is the second bird. So, but in GA we don't keep track, which is in the first, which is in the second, right? But here you have to. So this is PI best is actually the best ever location of the ith bird. So this difference says this is your current location, and this says, hey, you had the best far away over there. So try to go back to that. So this actually says try to go back. So there is a velocity component here that's trying to take you back towards your best ever location so far. But then you don't go 100% towards that direction. You modify it with a parameter called C1, again a parameter that you have to set, and a random number between 0 and 1. It's a random vector actually. Okay? So then you have that quantity. Third aspect is more of a social aspect, and that says PG is the best location of the whole crowd, the whole school, the whole swarm so far. It may not be that bird, but it may be some other bird which had the best fitness location. So if you think of on the sky, there is a fitness location. So let's say there is a food which is floating around, and all these birds are trying to get there. So which one ever came close to that location would be that PG location. And they may have overshoot and now coming back. So these vectors are pulling them back. Okay? You can imagine that way. So PG is that location. And then this is your current location. This is the difference. Again, you multiply by another factor C2 and a random number, a random vector. Usually they keep C1 equal to C2. So there are three aspects in between 0 and 2. Three aspects, momentum part, which is the velocity, cognitive part, which is your own, where own you are the best, you try to go back to that one, and social, you'll also look at the whole school and see where the best ever anybody had, you all try to go back to that one. So individually you now correct your current position, when you go to the next position, everybody's position is corrected, and then you correct again and again, and like that, starting from one initial configuration, you are moving towards your best point in the sky, right? So in case of an n-dimensional problem, you will be moving towards the optima. Question? Yeah. Cognitive part is your own part. So the bird's own location, which means if you are the 5th population member, you have to, and you are currently a 10th generation, you have to go back all the way till 0th generation. All population you have to store, okay? And then the 5th positions, you have 10 such positions, right? If you're at the 10th generation. Out of those 10 points, which one has the best fitness so far? That's your PI best. Individual best. For the 6th individual, it will be a different point. Okay? And PG is the best location of anybody in the population. So it's the global best, where you had the best location ever by anybody. So that is PG. And there is a component towards that. So there is a component of the vector getting towards the global best, component towards your own best, and the velocity by which you have come. All the three are combined. Here, these are basically weights. Weights of which one you want to give more importance, and that's what you can control here. Okay? Again, there are several versions of this. They multiply the whole thing by a vector, because sometimes what happens with this, you go out of your feasible area, lower bound, upper bound, because these are free form moving, so you can go out of that. And so there is a way they control that you come back and everything. So again, they call it, well, they don't call it an evolutionary algorithm. Let's spend 1 minute thinking about it now that you know the principles of evolutionary population-based methods. Is there so first of all, is this a mutation operator? If I try to call it an evolutionary algorithm, is it a mutation? No? Yes or no? Mutation definition is one parent you have to just perturb, one child you have to perturb. But here I see PI best, I see PG. These are not fixed members, right? As you move from 10 to 11th, your PG and PI best may have changed. So it's also evolving. Okay? So there are so many of them involved, 3 of them involved, xi, pi base pg, and also the xi's previous location. So there are 4 of them involved. So it's not mutation, it's more of a recombination of those points. If you go down into the actual core part of the algorithm in the x spaces and you analyze what's happening, it's actually not a mutation. So first of all, if I call it evolutionary method, this is not a mutation operator. This is a recombination operator. There is nothing I can put here as a mutation, right? It's not very clear. The mapping from crossover to, PSO to GA is not very clear here. But the population is there. They're taking some members and creating a new child. Okay, so it's kind of a mixed thing. So in one of the papers, we try to come up with an algorithmic equivalence of this as a GA. You can actually do, except that it doesn't remain as a Markov chain. You now have to take all these other populations into account. But you can write a GA where you can pre-specify a crossover operator and all that. And then we, through GA route, we then introduce a mutation operator, and that can come back into it. Elite preservation can come back into it. So all these that we know for GA can come through that equivalence route. And now you can have more and more operators, which will be difficult for me to write here. But if you make that connection, you are getting better and better modified PSO. So there is a reason for to do that. But the issue is that whether you call it evolutionary algorithm or not, you should try to understand what's going on. So you have a population, and the whole population is changed based on locations of good solutions. So there is a tendency to go towards the better solutions. There is no other selection operation. There is no explicit selection, you see. Okay? Because every individual is changed. So this has some merit. And if you then can write, okay, here is a PSO, which is a population-based algorithm. Here is a GA, which is a population-based algorithm. So you are actually coming out from the evolution and saying both these are population-based. Now and if I look at into the math, how each solution is updated in a mathematical way, can I see a connection? Because I gave you the SBX math, how the children are created, right? You remember that has P1, P2, and the beta Q and all that? I can write them side by side and see what's happening in that math space. If there is not much difference in them, basically the way we are presenting it is different, right? But at the core, they are identical or very similar. So there is a need for us to go into that depth and try to connect these algorithms. And this could be a very good research topic. I named this course as Optimization for Research and Innovation. So, and most of you are PhD student here, so you may be looking for some ideas. So these are some things I'm telling you really would make a big contribution if you can make some of these connections. And some of the things we have started already in our labs, but many of them are to be needed. I mean, this is just with PSO and GA I'm saying. How is PSO connected to DE, for example? DE connected to GA? Or there are other real parameter stuff, so you can try to come up with a common way of doing it. Will be a very nice thesis, actually. It will contribute quite a lot. Okay, so I think I'll stop here. Already taken 10 minutes past. One last question, yeah.
What is C1, C2 here?
It's a parameter. So every algorithm has its own parameter with which you can control the performance. So they keep it between 0 and 2. If you use less value, you are not giving importance to your previous bests. You are